Hello, everyone. We're glad to see you on the second day of Vilnius Machine Learning Workshop. We're really glad that you're able to join us on the second day. It's a workshop on deep learning, reinforcement learning, and causal inference. If we could see the slides already, please, that would be lovely. So that so it's a Vilnius Machine Learning Workshop. And if you could go on to the next slide, please. We are some housekeeping rules right from the start, just like yesterday. The stream is available on vmlv.live. We will be using Slack, Slido, and Twitter for communication during the event, just like yesterday. So please do log in on Slack for general announcements, discussions about the specific topics, and etc. Also, all of the questions, if we don't have enough time to answer them during the Q&A session, you can follow up on them on Slack. And we also do encourage people to check the introductions channel and introduce themselves. Now, you will also see the Slido, which we use for Q&A. Slido is integrated into our main website, and we will be also posting live updates on Twitter. So we very much encourage everyone to also be quite active on social media, spread the news, spread your excitement, and spread the kind of things that you find interesting, share it with your followers. Next slide, please. Now we continue with an excellent lineup of speakers. Some of them were already presenting yesterday, and the other ones will also present today. So we once again thank all of the speakers who agreed to participate in our workshop, and very much excited to hear today from Andrew Jason, from Carolina, from Audrunas, and from Virginia, who will be talking today. So very much looking forward to it. And next slide, please. And I believe the slides have not switched yet, but we would like to thank you, the partners and the sponsors who are also kind of participating in organizing this event. So now you can see the partners, the universities in Lithuania, as well as the organizations like Women Go Tech and Clear AI. So we want to encourage diversity as much as we can. And please do check out the partners. Now, if you go on to the next slide, you will see the sponsors of our event, like Vintent, Nascent, Biometric Designs, and yeah, it seems like our slides are slightly behind me talking. Yeah, there seems to be a slight delay in the. Ooh. There are some special effects going on. But anyway, we also wanted to announce the winners of the quiz and winners of the EML lottery for the yeah, I believe something is not going right with the stream at the moment. Could you please confirm that? Okay, just give us a second. We're trying to fix the thing with the slide share. Should be all good. Well, that's what happens when you try to do events live. So stay with us, and we're going to fix it shortly. All right. In the meantime, today we have already Andrew and Soren preparing to do the presentation for us as the first speakers. So they're getting ready, so stay excited for that. Meanwhile, we're trying to solve the technical difficulty with sharing the slides, and it seems like slides are slowly popping up back. So we will continue just in a second. All right, so slides should be popping up just in a second. Can we please get the slides up? Okay, we're still having an issue with slides, but we still are on time, so that's fine. Okay, slides, we can see the slides. So the slides are up. You can see the schedule for today. Now we would like to announce the tree planting EML lottery winner. So if we could get the slides for the lottery winners, please. Yeah, so Vintage EML lottery winners from the EML workshop, EML summer school in Budapest. It's Alina Rogalska, Rhys Thompson, and Saulius Tautvaisas. These are the 3 winners who won the lottery. So please do reach out to us, or we will reach out to you. We have the contact details, so we'll find you and find out what is the best way for us to share the books with you and send them to you. So that's as far as EML lottery. Now we go on to the announcement of the quiz winners. So the quiz winners that we were running yesterday, they also get the books. The winners are Mantas Bandonis, Chandra Muli Kota Kota, and Eliza Olaru. So these are the 3 winners from yesterday. If you have any questions regarding how we can get in touch with you, or just please know that we will try to get in touch with you and try to find a way to give the books to you. Now, if we can carry on to the next slide, please. Now, the next slide is going to be about the special thing that one of our sponsors is doing, is providing every participant who participated in the summer school as well as in the workshop with a personal tree. So in the spirit of sustainability, for every person who registered, Vinted is going to plant a tree, and you will receive a named certificate with the description of where your tree is in the name in your name. So this is quite exciting. So please watch out for a notification that there is a tree planted for you somewhere. And you can also follow up on Slack if there are any questions. Now, this is just one of the events that we are organizing together with EML as a Lithuanian AI association. We will also be announcing soon paper reproducibility challenges, which will be announced on Twitter. And there will be a conference in Lithuania, AI Boost conference in November. So please do watch out for that as well. Now, there are other events that we are preparing in terms of reproducibility challenges, like reproducibility challenges for causal inference and reproducibility challenges for reinforcement learning, as well as the challenges, hackathon type challenges. So please do stay in touch with us on Twitter, and you'll get updates about these events. And next slide. Okay, so it looks like that's all in terms of the announcements that we're going to make. In terms of the time, I believe we're ready to transition to the presentation by our first speaker, Andrew Jason and Soren, who joined us today also. We are very lucky to have them too, from University of Oxford Machine Learning Group. And they will be talking to us starting almost immediately. If we could just have a few seconds to start sharing the slides.
Can you hear me?
Yeah, we can hear you. If you could just probably switch to full screen, that would be great. Excellent.
Looking good?
Yep.
Very nice to meet you in person, Jeff. Talk a few times via email and on GitHub. So really pleased to be here today, and thanks for the invite to give this talk.
Yes, thanks. Thanks for having us.
So today we're going to be talking about some work primarily that we did for NeurIPS 2020. The paper that we will be basing this talk on is called Identifying Causal Effect Inference Failure with Uncertainty-Aware Models. This is joint work by Soren and I, and supervised by Uri Shalit at the Technion and our supervisor, Jaren Gao. So the structure of the talk today is going to follow 3 parts. So in the first part, I'll do a bit of background on personalized decision-making, applications to healthcare, how do we learn causal effects from observational data, what is observational data, using causal effect estimates in decision-making, and when we should trust those decisions. A little bit of background on Bayesian deep learning as well. And then we'll pass it on to Soren to go over and how we sort of took a Bayesian deep learning approach to address some of the issues with identifying treatment effects. And then we'll finish that up with some follow-up work that we've worked on. So without further ado, let's start by getting into personalized decision-making. I was having a little bit of issues with connectivity yesterday. Maybe Soren, give me a wave if things start lagging again or anything like that. So personalized decision-making is sort of concerned with the types of questions like, should I take an ibuprofen or hydrate to relieve my headache? Should I brake or turn to avoid an incident? Or should I study engineering or computer science, machine learning? In general, there may be population level trends that will help one make these decisions. For example, maybe on the whole, it is better to take ibuprofen, maybe it's better to brake, or maybe it's better to study engineering. None of these options are scientifically validated. But what we're interested in with respect to personalized decision-making is specifically the best choice for you often depends on you and your environment. So what are these environmental factors, or what are the characteristics about you that are going to make that decision the best choice for you? For example, if you are a professional driver and you find yourself in a situation where you are about to avoid an accident, maybe it makes more sense to turn to avoid that accident. But if in your environment there is a pedestrian, then turning might be the wrong choice and you might want to brake instead. Before we go on, some interesting reading that I find that really explores sort of the problematic aspects of making decisions on behalf of others or for others based on data that is biased to a population that doesn't represent them, or invisible women, and algorithms of oppression. Interesting work that I would recommend following up on. So now let's take a second to look at, we're going to focus a little bit at moving from personalized decision-making in general to sort of the healthcare example to motivate our talk today. So I'm having real trouble switching slides. Okay, just have to wait for it. So I'm sure many of you have heard a lot of buzzwords these days: personalized healthcare, precision medicine, precision healthcare, targeted treatments, all of these things. And this is really focusing on how you as an individual are going to respond to a given treatment. Right now, sort of research in this area and even development of solutions is sort of being driven by the increasing accessibility of large-scale clinical data. So things like the UK Biobank, for example, where you have like 500,000 individuals. For a subset of those individuals, you have imaging data from brain imaging or from retinal imaging. You have genetic data. You have clinical variables. All of these sorts of things where you want to sort of learn about maybe causal mechanisms with respect to some given outcome. Of course, machine learning, something that shines when we have this data access, and really spurring a lot of work towards sort of learning from this data. There are some challenges associated with learning from this data because a lot of these data sets are observational. So they are collected from individual medical centers, like the UK Biobank, or they can be collected directly from you, say via a wearable smartwatch or device. Sorry. So what exactly do we mean when we say observational data? And So let's take a second to sort of go into that. I don't know why my slides are so laggy. Okay, so observational data is typically made up of so yeah, there's three sort of aspects to an observational data set. Right now on the right, we're just going to sort of look at a 1D example for illustrative purposes, but we have sort of these high dimensional covariates. These are descriptors of you. So this can be imaging, electronic health records, your genetic profile, various different things. Then we also sort of look at, we're sort of focusing on this case where we're looking at binary treatment. So individuals in this observational data set for which we have measured covariates also have a treatment that would be assigned after the variable has been measured. So that's a binary treatment here, which sort of partitions individuals into the control group, those who didn't receive treatment, and the treated group, those that did receive treatment. Then the outcome, for example, years survived after chemotherapy treatment, can be recorded after the treatment is administered. A fundamental difference. So a lot of this might be recap after Brady Neal's talk yesterday. But so he probably brought up maybe randomized controlled trials or experimental data, as well as observational data. So just as a recap, a fundamental difference between observational data and experimental data for randomized controlled trials, is that the treatment assignment, whether or not you belong to the treated group or the controlled group, is typically not random for observational data. So in that case, we are going to see associations between the covariate and the treatment. Here we see as the covariate value increases, we have a greater propensity, a greater probability that an individual will be assigned to the treated case. And also sort of relationships between the covariate value and the outcome. So as we have this trend, this very clear trend between the covariate value and the outcome. When you have a covariate that sort of satisfies these two properties, causal links between the outcome and the treatment, we call such covariates confounders. And if we want to learn something about causal effects in this model, we need to control for these confounders. So what can we learn then from observational data with respect to making personalized decisions? So the causal estimate of interest, when we're talking about personalized decision-making or individualized treatment effects, is the conditional average treatment effect. And so this Kate, the Kate is defined as this expected difference in potential outcomes at a measured covariate value. So let's take a second to sort of break down this equation. Conditional average treatment effect. So let's look at treatment effect. This is sort of the difference between potential outcomes. Potential outcomes are these causal quantities, sort of reflecting how would you respond to treatment were you treated, so Y1, or how would you respond to treatment were you not treated, Y0. So that's treatment effect, average. We're taking an expectation of this difference between the two potential outcomes. And conditional, this average is conditioned on some measured values, some representation of you. I hope that is clear. So how do we use the Kate for personalized decision-making, or how can this be used in an ideal situation for personalized decision-making? So a simplified treatment policy would be just to treat an individual if and only if their Kate is positive. So if the treatment effect, given their covariate value, is greater than 0, we say treat. Otherwise, do not treat. So equivalently, we can say don't treat if and only if the Kate is negative. But what if we can't identify the Kate? What are some reasons why we wouldn't be able to sort of know about this Kate and learn it from observational data? So as I said, the potential outcomes are these causal quantities. And as these causal quantities, their difference is unobservable. In effect, I can only observe one of these two potential outcomes, the potential actual treatment that was assigned to this individual. So it is desirable then, or it's necessary really, to express Kate in statistical terms, where we move from these cost estimator for the Kate, which is going to be an expectation of an outcome, the observed outcome that we see, or the distribution of the observed outcome, the distribution of the observed outcome for each covariate value X. So if we look at sort of a non-parametric approach to this, we can get these conditional averages or conditional expectations. One for the treated group, where we get this line, purple line, that's just the mean of these treated group values. One for the control group, which is the blue line here, which is the mean of the observed outcomes. And this gives us our treatment effect in purple, which is just the difference between these two expected outcomes. However, the Kate estimator is not, or the Kate is not identifiable through the statistical estimator without further assumptions. So we have to assume that consistency, that our observed outcome, Y, is actually corresponding to the potential outcome of the assigned treatment. We have to assume, so as we talked about earlier, about the fact that observational data is confounded, we need to include all of those confounding variables such that our potential outcomes are independent of the treatment when conditioned on those confounding variables. If all confounding variables are not included, this can result in a biased Kate estimate. And finally, which is going to be sort of the focus of this talk moving on, the overlap assumption, which is that for any measured value of X, our propensity for treatment, whether that treatment be controlled or treated, is going to be greater than 0 or greater than epsilon in a relaxed case. So I think we can already sort of get a sense at looking at this figure that if any of these assumptions are viable, well, what can we say about the Kate? I think we should be uncertain about the Kate. So in this image to the right now, in these blue boxes, we sort of are highlighting these regions where overlap is not satisfied, where, for example, we only see controlled examples on the left-hand side of the figure, and we only see treated examples on the right-hand side of the figure. So how can we calculate that difference in expectations? So now let's talk about Bayesian deep learning. So this is a way. Let's just take a second here. So parametric models can estimate statistical quantities. So let's just focus on the treated case here. So the expectation of the outcome, given that we observe treatment equals 1 and our measured covariate value X. So here on the right-hand side, we're seeing just the statistical mean of the observed data points, a non-parametric estimate. So neural networks, the weights of a neural network induce a function that estimates the expected conditional outcome. So this expected conditional outcome, estimates the expected conditional outcome. And this function that is induced will extrapolate beyond that data manifold. So it gives us a sort of continuous function of our conditional mean in this case that will extrapolate beyond the data. If we use a maximum likelihood approach to learning these weights, then we get one functional explanation. But a question becomes, what should this function look like when we extrapolate outside of the support of the training data. And now we can turn to sort of a Bayesian deep learning approach to instead model a distribution over such functions. So instead of having one functional explanation of we have multiple functional explanations of the data that would each ideally explain the observed data equally well, and give us the opportunity to, when we extrapolate beyond the support of the data, so they agree with each other when they're on the support of the data, but when we're extrapolating beyond the support of the data, they ideally should disagree with one another. So that measure of disagreement or epistemic, that we can express our knowledge or lack of knowledge about covariate values through measuring sort of how much the functions disagree with each other at a given covariate value X. And we call this, well, in the literature, it's called epistemic uncertainty, how much the functions disagree with one another. Become more uncertain the more they disagree. We can also sort of think of this in terms of a classification problem, which I think is going to maybe be more intuitive for the next section. So we can have, instead of doing a regression problem in the last example, we can just have an observational data set where the outcome is health improved, health did not improve, which we can see here. Again, we can learn a function to predict that. A Bayesian model learns a distribution over such functions. On the training data manifold, those functions agree with one another. Off the training data manifold, they do not agree with one another. And we need this measure of epistemic uncertainty, which measures how much they disagree with one another. And we can use that measure then to sort of tell whether we are predicting for a data point, a new data point that lies within the data that we've observed, within the support of the training data, or if it lies outside of that training data support. So now I will pass that on to Søren to talk about the methods.
All right. Yeah, thanks for the first part. So I'm just going to go through some of the main ideas and leave out some of the extra details that you can find in the paper. Yeah, let's go on and continue with this example Andrew just introduced. Except now we have two graphs here. We're going back to the causal setting, where we have on the top the untreated control group, and on the bottom the treated treatment group. And each of these dots or circles, of course, represents a data point. So, and the sort of the line going through them represents the ground truth function, which gives the probability that a given point will have a positive outcome, or an outcome of 0, 1 or 0. So in this example, we've designed it so that overlap is satisfied. There's no problem, because for every sort of treated point, we also have untreated points close to it. And for every untreated point, we have treated points close to it, so that everywhere where the data set has coverage, overlap is satisfied. Next slide. But now we've shifted the data a little bit along the x-axis to create a situation where overlap is violated in this red area. So you can see in this area, you only have untreated individuals and no treated individuals. So it's obvious that we cannot really know what the Kate would be for these individuals. Now, as Andrew sort of talked about, with standard methods, if we estimate a function with maximum likelihood, we would just that function would just extrapolate in some way and then give us an answer about the Kate anyway. without highlighting to the user that maybe this answer is unlikely to be correct in this area. Next slide. Now, when we instead take this Bayesian deep learning approach, fitting Bayesian models to each of the groups, then we can see that this recognizes the data problem we have here. Starting first, next slide, with the region on the right. So this is not yet, I'll get to overlap in a second. This is not the no overlap region. This is just a covariate shift region, because we don't have data available for neither the control group nor the treatment group in this area. And so obviously we can't know what the case should be here, unless we would be unrealistically good at extrapolating. So yeah, in the bottom graph, we've sort of quantified, given a measure of this disagreement between functions that are compatible with the overall data. I'll give that in sort of quantitative terms later, but what you can see is the purple line at the bottom, that's epistemic uncertainty, the disagreement for the treatment group. The green line at the bottom is uncertainty for that one's for the treatment group. And then the black line quantifies the uncertainty in the difference on the expected outcomes, which is the Kate. So we can see that here's this sort of gracefully deals with this data problem we have in this area. Now let's move on to the no overlap area. You can see here that it also, this functional disagreement through Bayesian method also recognizes the uncertainty here. So yes, for the untreated group, we do have agreement between functions, so there's not much uncertainty. But for the treatment group in the middle graph, we lack the data. We have an overlap problem, and by illustrating this way, you can sort of see that the overlap problem we have here can be thought of as a covariate problem, but it's only a covariate shift for the green for the treatment group in the middle, so that we want to argue partly with this paper that you can just bring to bear the whole suite of methods that exists for addressing covariate shift problems and apply them to this overlap problem, because that's a covariate shift problem in disguise. Let's go to the next one. Right, so in this area, we can now quantify epistemic uncertainty in the Kate. And what do we do with that? Well, we can use it to define a policy for when we withhold or defer automatic treatment recommendation, because there's insufficient knowledge about an individual. Next slide. Right, so let's actually quantify this epistemic uncertainty. So recall that the Kate is the expectation of y1 minus y0. Now, to quantify uncertainty, we look at the variance of y1 minus y0. And we decompose that just to show the connection between the different sources of uncertainty that are at play here. So on the left side of the equation, I've written out the variance of y1 minus y0. And you can see that this, at the bottom, you see this probability. You can see that there are 4 sources of uncertainty. First, parameters, omega 0, omega 1. And the second one, uncertainty about the potential outcomes, y0 and y1. So the sort of Bayesian approach brings in this uncertainty about the parameter, sort of normal maximum likelihood approach. Now we can decompose this whole variance on the left. and you can see that click. The term at the bottom is actually the one we care about. So this is, we wanted to uncertainty indicate, and you can see that it's mu0. This is just our estimate of the Kate. And so this term is really quantifying the thing we care about, which is uncertainty in the Kate. And this is an epistemic uncertainty. We call it that because it's a lack of knowledge, meaning it can be resolved with seeing more data. So if we were to see a lot of data in all the regions of the input space, then this uncertainty would dissolve. That's what makes it an epistemic uncertainty. The other term at the top, that's what we call, it cannot be resolved through seeing lots of data. That's why we call it aleatoric uncertainty, coming from dice in Greek, meaning the throw of a dice. You can never predict what the dice will come up with, even if you've seen a million dice rolls before. And luckily, it turns out we can ignore this uncertainty because we are only interested in the Kate, which is the expectation over the potential outcomes y1 and y0. So the inherent stochasticity in y1 and y0 can be ignored because we are taking the expectation over them. And this is handy because it's actually impossible to quantify this aleatoric uncertainty term, because it would require us to both observe both potential outcomes, y1 and y0 for the same individual at the same time, which is impossible because you can only ever treat them or not treat them. But this luckily factors out. So we're going to use this term at the bottom, variance of the Kate, going forward to defer decisions. So let's go to the next slide. Right, so given that we have this epistemic uncertainty, how do we decide which points to defer? Well, in principle, when the Kate uncertainty exceeds some threshold, recommending a treatment would be unsafe. So how do we set the threshold in practice? There are two sort of main ways to do that. One is it can just be given by medical authorities. So for example, for tasks like diabetic retinopathy, there will be usually in many countries a medical authority that says your probability of false positive should not be above such and such. Your probability of a false negative should not be above such and such. And you can work backwards from there to set the right threshold of the epistemic uncertainty. And the second way to do it is to set a threshold is to use a domain expert who can put cost values on false positives and false negatives. And for example, in treatment of COVID, I'm not an expert, but as far as I know, people are often given antibiotics in the ICU because COVID patients also tend to acquire a bacterial pneumonia. And antibiotics are given because there's not that much harm to giving them. They usually don't kill people, but not giving them when somebody actually has a bacterial infection, that can kill them. So the cost of a the cost of treating someone that doesn't need to be treated here is much lower than the cost of not treating someone that would need the treatment. And so again, from these costs, you can work backward to set a threshold on when you should defer points for sort of expert evaluation, because we can't trust our automatic system. This is sort of our approach. I'll also say that sort of existing methods usually don't use epistemic uncertainty, but instead use the propensity score. So recall that the propensity score is the probability of treatment for a given individual. So, high propensity means that this individual is very likely to be treated. And we can defer points because they violate overlap assumption when they have a very high propensity, close to 100% or close to 0, very low. Next slide. Cool. So let's get into some results. So because there aren't that many really high-dimensional data sets weren't in the causal inference yet, we started by designing a benchmark, which is based on the MNIST data sets, which is very common in machine learning. It's this classification of handwritten digits. And we adapted it for our purposes to turn it into a causal inference task. And on this left graph, we sort of illustrated some of the problems that the propensity-based deferral approach runs into, which are handled more gracefully by epistemic uncertainty-based deferral. So click, please. So this is a propensity histogram. On the x-axis, we have, propensity. On the y-axis, we have how many individuals have that propensity. And in this area on the left, we sort of used one digit of the MNIST data set. I think it's the digit 9, where we have loads of data, as you can see by the high big hump. But they have a pretty low propensity, so most of them are blue. They're not treated. So the propensity-based rejection method would sort of defer these points because the propensity is very low. But actually, what it doesn't take into account is that we have loads of data here. So despite the low propensity, we can still estimate the Kate because we have so much. We still have like a good number of treated individuals, even though most of them are not treated. And this gives us low epistemic uncertainty, so we're not going to, distrust our model here. Next one, double click. Yes, so this middle region, these are where most of the sort of digits lie. And they have this middle trending nice 0.5 propensity. So our propensity-based methods will definitely like these points and assume that we know the outcome, that we know the Kate here. But actually, here we have very little data. So we shouldn't actually be able to know the Kate. So you can't see that in this histogram because it's a whole bunch of different classes, image classes, put into this one region of the histogram. But actually, each of those classes has very little data. So the Kate is very uncertain. And that's what epistemic uncertainty quantifies. Yeah, and then finally, we have a third region, double click again, where the propensity is actually 0. The propensity is 100%. All the individuals are treated. And here we really can't know the Kate, and we're going to see that both epistemic uncertainty recognizes that because it recognizes the covariate shift for the control group. And of course, the propensity methods also work well here. Moving on to the graph on the right, these are just results in terms of accuracy. So we have number of errors, and we see on this data set, withholding points with epistemic uncertainty as the green line achieves a much lower error rate than propensity-based methods. And in fact, the propensity-based methods do somewhat worse than random, which may be surprising, but it makes sense if you look at if you're aware of the problems that I just pointed out there with the propensity method. Now let's move on to some of the standard causal inference-based benchmarks. So these are IHGP and ASIC that we use here. IHGP is sort of probably the most well-known one in causal inference. And we see the exact same pattern here. Each time the green line, the epistemic uncertainty, gets a much lower error. And we've, oh, by the way, I should have said on the x-axis, we're sort of sweeping over how many points we defer. So, for example, in the left graph at 40%, if we can see if we defer the 40% points with the highest epistemic Kate uncertainty, then we've basically reduced the error on the remaining points to almost zero. So this sort of goes to show how common sort of problems like overlap and covariate shift, probably mostly overlap, are even in a very nice curated data set like IHGP. It is still the case that we can achieve much lower errors by letting the automatic system do the points where the automatic system knows what it's doing, and then leaving the other points for maybe an expert or a different system that is not so personalized. And on the middle graph, we've designed a variant of IHGP that has covariate shift. Again, you can see here that the uncertainty-based method still works. And then finally, it also works the best on the ASIC data set on the right. The benefit is a bit less extreme here, but there's a clear improvement in the error from rejection or withholding with epistemic uncertainty. Next, please. These results that I just showed, we're just replicating them across a whole bunch of different, at the time, state-of-the-art causal inference models. So models like DragonNet, HARNet, T-Learner, and these are all deep learning methods, except the top one, which is Bayesian additive regression trees. And you can see across all of the methods and all of the data sets, uncertainty-based deferral does better than propensity-based methods and random deferral. All right, that was my part. I think maybe we can. You want to do some more slides, Andrew, right? So we can skip this one.
Oh, you don't want to just conclude this bit?
All right, let's do it. I hope we have enough time. Yeah, so I'll just briefly conclude. Observational data, especially when it's high dimensional, often violates the overlap assumption. And additionally, treatment recommendation is made for individuals who are different from the training data, for example, because the training data comes from some region or hospital. And this is called a covariate shift. A good causal model should communicate both of these problems to the user. And for both of them, epistemic Kate uncertainty provides a unified approach to identify these failures by keeping a Bayesian posterior over the weights of our model. Did you want to take it over from here, Andrew?
Sure. Thank you very much for that part, Soren. Also, I see that there are some really great questions in the chat. I'm just going to finish these last two sections on related work, and then I'd be really happy to get them. And if more people have questions, please submit them to the Q&A. So this work was really focused on sort of quantifying our uncertainty about conditional average treatment effects when the overlap assumption is violated or when we have experienced covariate shift. So in that case where we are very uncertain about a point, we're saying a deferral should be made. And this deferral can take many forms. If it's a very time-sensitive application, then maybe that's deferral to an expert. Maybe that's deferral to a safe policy. But if there's more time, maybe we can do better. Maybe we can learn more about those points that we don't have high certainty about. And one of sort of a follow-up direction that we took was looking at how can you reduce that uncertainty, and specifically at looking at reducing uncertainty due to non-overlap or to covariate shift. So this work was submitted to the Neglected Assumptions in Causal Inference workshop at ICML in 2021. It's called Causal Bald, Deep Bayesian Active Learning of Outcomes to Infer Treatment Effects from Observations. It's a mouthful. This is a co-work with Paniotis in our lab, as well as Joost van Amersfoort and Andrew Kirsch, and again, supervised by Yuri and Yaron. So this work really is focusing on how do we get a sample efficient strategy to acquire outcomes for observational data. So again, similar observational setup where we have our observed, we have our two groups are treated at a control. We want to get outcomes in those groups, and we have a pool set that is just consisted of covariates and assigned treatments. We want to acquire labels for those, and we want to sort of efficiently explore that pool set so that we're acquiring points that are going to be maximally informative about our treatment effect. So a very naive approach would just be to randomly acquire points. And this is interesting in a sense that randomly acquiring points from your pool set, examples of treated or untreated measured covariate values, will lead to this unbiased sample of the pool data, but that might not be what you want when you're looking for data efficiency, or even for finding being accurate across the data, because random sampling kind of biases the acquisition of your training set towards the modes of this distribution. So we get an unbiased sample of this pool data set, but if there already exists bias in that pool data set, then we're kind of amplifying that, or not amplifying it, but we're not mitigating that bias by doing random sampling. And as we can see, we sort of are very certain in the bottom pane of this graph, we're very certain around points near the mode of the data in the middle and accurate. But as we move from that mode, we become more uncertain about the treatment effect, the Kate, and actually less accurate about the Kate as well for a given number of acquired points. So we take instead an information theoretic approach to sort of efficiently explore regions of the pool data and focusing on those regions where overlap is satisfied, but also sampling points for which we're more uncertain about. So the points that are going to reduce our uncertainty the most, or result in a maximum information gain, which we sort of express as the information gain between our parametric estimator of the Kate and the observed outcome, or the observed potential outcome, the potential outcome that we can observe given that T has been assigned. So that's one sort of direction of work. This is a really active field of exploration. So we talked about the three assumptions: consistency, unconfoundedness, and overlap. So another assumption there was unconfoundedness. So how do we incorporate beliefs about hidden confounding in our Kate estimates? And this was work again with Soren and I that was accepted to ICML 2021, called Quantifying Ignorance in Individual Level Causal Effects Estimates Under Hidden Confounding, another mouthful title. And here we sort of looking at, in addition to incorporating uncertainty due to insufficient overlap into personalized decision making. So again, this is sort of looking at that first work, the work that we presented today, where we want to be uncertain when there's not overlap or there's covariate shift. We'd also like to incorporate whatever ignorance we might have about the treatment effect due to the possibility of hidden confounding. So as we can see here, hidden confounding, what hidden confounding does is induce a bias in our Kate estimate. If we have an X that affects both the treatment and the outcome, and it's not included in the model, this is going to bias our Kate estimate, showing a difference between the true Kate, the black dashed line, and the predicted Kate. And this is something that epistemic uncertainty cannot reflect. This bias. This bias is not contained in epistemic uncertainty alone. The model will still be certain where there is a lot of examples in the data, and uncertain where there's not, but it doesn't say anything about this bias. So we sort of extend work by Angela Zhao, Nafi Callis, and others to make sort of a scalable, unified approach to model both our uncertainty that arises due to our belief in hidden confounding using a causal sensitivity model, and this epistemic uncertainty to give us this Kate interval for which we can use in so I guess I will stop there and we can take a look at the questions. Some very good questions. So Sarah asked earlier, what do you think of trans and non-binary people who have been mistreated by doctors over the years? And I think this is a really, really interesting question. And I think that's a very real problem. I'm not an expert on that. And I would really appreciate any reading material that you might have, but I think it's a terrible problem, and but I don't know if I can say anything intelligent about it right now, because I'm unfortunately not very read up on all the problems that exist. So maybe I can pass this one to you, Soren. Dimitri asks, could you please elaborate on epistemic and aleatoric uncertainties and how they connect to overlap and underconfoundedness assumptions?
Yeah, sure. Maybe we can go back to the math slide. Well, let me first of all maybe define the aleatoric uncertainty a bit better than I did before. So if you look at the first term on the right-hand side here, what we have is, and especially the y1 minus y0 part, right? So what where the variance here comes from is that the outcome for any given patient is not deterministic, or at least it's not modeled as deterministic. So even though we've conditioned on knowing the parameters, right? You can see here we're conditioning on mu parameter 1, mu parameter 0. Even though we sort of assume that we know the ground truth function, there's still some uncertainty in the actual outcome, because there's some stochasticity in how people actually respond. So you can only basically know the expectation of the response, not the actual response for any individual. So that's why we call it aleatoric. It's like inherently stochastic, and we cannot learn it even with infinite data. So this uncertainty, I would say it's not so much related to overlap, and that's lucky for us, because it means we don't have to model it. What is related to overlap is the epistemic uncertainty. That's the one at the bottom, and that stems from uncertainty about the true parameters that generate the outcome distribution. And yeah, I guess going back to what I said earlier, when we have an overlap problem, we're going to get some epistemic uncertainty. So specifically, let's say the overlap problem we have is the treat that for a given sort of set of covariates or a given point at the x-axis, we've seen a bunch of treated individuals with these characteristics. Or let's give an example, actually. Let's say, we're talking, we have a covariate that says, whether somebody is pregnant. And now we have a pregnant woman in our praxis, and we want to sort of make a personalized treatment decision. Now, it's probably the case that that in our training data, we've never seen a treated pregnant woman, because for a lot of different treatments, there's just a general like consensus not to give them to pregnant women because we don't know the consequences for the child especially. So we've probably never seen how this treatment works on a pregnant woman. But if we just use a likelihood-based or maximum likelihood-based model, it will probably have some confident answer about what the outcome will be. And so, you know, we're going to get, if we use epistemic uncertainty here, we're going to have this parameter uncertainty, which tells us that for the treatment group, we don't know basically how this pregnant woman will respond to treatment. So that'll give us some like different possible outcomes, and then we have epistemic uncertainty in the treatment in Y1 basically, or in the expectation of Y1. So how do we relate to unconfoundedness? That was, I think, a different part of the question. And well, I guess it's I'm not sure if this is a solved question. We've been working on it a bit. Maybe Andrew can also chime in here because we have sort of tried to quantify or try to conceptualize really better uncertainty that stems from confoundedness. So when there is a confounder that is not part of X, one that's unobserved, that should give us some sort of additional uncertainty in the treatment effect. But this uncertainty is, I think, not very well understood how to model it. And I guess I would say it's different from epistemic uncertainty, and it's different from aleatoric uncertainty. Although, I mean, it's a bit of a semantic question, because you could define aleatoric uncertainty as including uncertainty that stems from not seeing all confounders, because, you know, this is also confoundedness is also a problem that stems from that cannot be solved by seeing lots of data, or you need to, so that sort of fits the aleatoric uncertainty concept of that a bit. But, you know, whether this is aleatoric uncertainty or not is, I would say, essentially a philosophical question. Yeah. Do you have anything to add?
Yeah. I mean, we've definitely been thinking about this a lot, and it's a really interesting question. How aleatoric uncertainty, well, what uncertainty relates to sort of hidden confounding. And I think that, so there will be a component of the aleatoric uncertainty that in Y, in the outcome itself, in our ability to predict the outcome, stochasticity in the outcome, that will be due to an unmodeled variable, due to model misspecification. The tricky bit is, well, one of the tricky bits is, how do you know if that is coming from a hidden confounder or not? And so there's a very interesting and conceptually challenging sort of relationship between how this is affecting uncertainty in both our treatment assignment and outcome, but I don't totally understand it yet. And there is the fundamental problem of the other part that's very difficult, is just we don't observe the difference in potential outcomes. So we can't really, without further assumptions, we can't say anything really about the variance of Y1 minus Y naught. Like you could take a very, you could take a very wide bound on that uncertainty and say Y1 and Y0 are independent, so I can just use a sum plus of these two uncertainties to say this is going to be my range due to possible hidden confounding, but that's a very, very wide bound. That's basically the worst case assumption. Because we don't observe that difference, we can't really model that interaction. Maybe we can move on to another question. So that was from Dimitri. So Oksas, sorry if I'm mispronouncing your name, let's assume that you have two hospitals that don't want to reveal their data and do their own Kate modeling. Would it be possible to combine two separate Kate estimates into a single unified Kate estimate? I think that's a really interesting question as well. So I know that there is some work, and I wish I had direct citations there, that looks at modeling our uncertainty in the Kate using sort of a bootstrap method where you would train individual models on bootstrap samples of the data. So I feel like that's kind of akin to having different hospitals and then maybe doing some sort of model averaging over that. I think there are probably a lot of issues that maybe I haven't fully thought out of some failure modes there. But Soren, do you have any further thoughts on that question?
Yeah, I mean, it's actually a very interesting question. I mean, it very much sounds like a differential privacy question. So maybe, maybe this is actually an interesting idea for a paper to extend differential privacy methods to the sort of setting where we're trying to train a Bayesian model. So I think in differential privacy, you would basically have this kind of question where you're trying to train a model on, different private data sets without sort of having to share those data sets between like different parties. And then at the end, it seems to be possible to get out a model. Maybe you pass the model around to the different stakeholders or so, or maybe like you share a sort of anonymized version of the data set where you add a bunch of noise to the data. And then you train a model on that anonymized or noisy data set. But yeah, I'm not sure if it's possible yet to do that while also preserving good uncertainty estimates using some Bayesian deep learning approach or so. So that'd be actually pretty interesting. And if not, then maybe, somebody should do it.
Cool. And we have a question from Dimitri. So if we go back, could you please go over some data sets used for causal inference benchmarks? Are there ImageNet kind of data sets for causal inference? I suppose the best data set would be a data set from an actual RTC. Perhaps, if we go back to this slide here, I think that there was interesting work recently. Okay, so first of all, we sort of showed a few examples there. So IHDP is definitely one. This ASIC 2016 data set is definitely one. There's this jobs data set, which sort of uses, so not jobs, but there's a twins data set that uses twins to sort of have non-synthetically generated potential outcomes. So that's sort of one way to go around it. But there was a really interesting work at this Neglected Assumptions in Causal Inference workshop by Alicia Kurth, who's a student in Michaela van der Schaar's lab. I think it was called How Great Is Your Kate or something like that. And that is really, I would suggest reading that paper. It's sort of like going into the issues with benchmarking Kate. A lot of them that we're using are semi-synthetic, so the outcomes are generated. How does the inductive biases, that paper explores how the inductive biases of different models are going to cause differences in performance that may not be sort of genuine in benchmarking. Would ideally RCT data be what we want to validate on? I'm not sure. Soren, do you have any thoughts on that?
I'm also not sure.
But hopefully that gets at your question. It's an interesting thing. I haven't really thought of whether or not RCT data would be the best to use for benchmarking. I could see potential problems with it if they're a small sample size. Could very quickly overfit to those data sets. I really have to think about it more. Jeff, do we have till 6? Sorry, I'm in Eastern.
Yes, we have still a few more minutes. We have 5 more minutes until the break, and then we're going to a 10-minute break after that.
Okay. From Dimitri, could you please describe on some of the other methods you had in the table, DragonNet, TarNet examples? So I can go back to that slide. So we looked at several different methods here. So BART was very standard Bayesian baseline that uses Bayesian additive regression trees. It's not really well suited, let's say, for high dimensional data, large sample data, but it definitely a necessary baseline, given that we want to it can quantify epistemic uncertainty as a Bayesian method. Then we sort of looked at different, we made Bayesian versions of some of the state-of-the-art, let's say, neural network models at that time. So you have these classes of meta learner, S learner, T learner, X learner. We just looked at T learner in that case, which is basically we took 2 neural networks and each would be trained on either the treated cohort or the untreated cohort, and you get the difference. And they're 2 Bayesian neural networks, and we would get a distribution over Kate by sort of taking the variance over the output predictions of those 2 networks, expected output predictions of those 2 networks. TarNet is a neural network approach that has sort of a feature extractor, and then after the feature extractor, it's similar to a T-learner where you have 2 branches of the neural network that are predicting for the treated and untreated group. Then we looked at an extension sort of TarNet, which is the counterfactual reasoning network, which has a penalty term on the intermediate representation to promote overlap between those 2 representations. So it will, where the TarNet doesn't have any constraint on the intermediate representation before you get the 2 heads of the network. This will say, I want the distributions of these I want the distribution for the intermediate representation of the 2 arms of the trial to overlap with one another. So there's something quite interesting here, that method did not do so good. It did quite bad on the high dimensional data set, the way we set it up. And I think that some of the in high dimensions that can cause some digits to kind of overlap with each other that they shouldn't. So it kind of loses, it could make 2 different subsets if there is completely no overlap, kind of map to the same point, which might be problematic, but we didn't go too deep into that. So that's something that I think would be interesting to follow up on. DragonNet kind of does the opposite of CFRNet in that it has an intermediate representation that is also used as input to a linear regression, a logistic regression of the treatment effect. So it actually linearly separates the data of the intermediate representation. And finally, Bayesian CVE, which is an extension of CVE, which is a causal effect variational autoencoder, which is a method that is going to try to extract representations. So it treats X, we say X is going to be proxies for latent confounders, not totally unobserved confounders, but latent in the noisy proxies that we observe. And it will learn a representation of the latent confounders for which to have your model going from Y and T from those latent confounders. So hopefully that answers your question. There's lots of other models, but these are the ones that we focused on.
So
does the pro? Oh,
If
sorry.
maybe in the interest of time, we probably should wrap up with the questions and carry on with the rest of the questions on Slack. So I see Soren already joined the Slack. So if you could join Slack, Andrew, that would be great. And then people could continue asking those questions to you there. But other than that, excellent presentation. And thank you so much.
Oh, thank you very much for having us.
Yep.
Thank you.
Excellent. So now we are going into a 10-minute break. And we will be back in 10 minutes with a talk from Virginia on causal Bayesian optimization. So have a great 10-minute break, everyone. Hello, everyone. We're back after the break. Pleasure to see you all here, and it is especially my pleasure to introduce Virginia here to you, who we've met with at Warwick University, because we both work with Theo Damoulas. So yeah, without further ado, I'm going to pass my microphone to Virginia.
Thanks, Jeff, for the introduction. Hi, everybody, and thanks for joining this session. So, as Jeff said, I'm a PhD student at the University of Warwick. I'm about to finish my PhD and also visiting student at the Alan Turing Institute. I'm working with Theo Damoulas, and today I'm going to be talking about causal Bayesian optimization, which is a framework that we proposed a couple of years back at this point. And I'm going to also be talking more generally about how causal Gaussian processes can be used for causal decision making. I believe this topic is very much related to the things that you've seen in the rest of the workshop, but feel free to interrupt me if there are some aspects of the basic that I'm not covering and you haven't seen it in the past. So what do I mean by causal decision making? So with causal decision making, I refer more generally to the idea of integrating causal consideration into a choice process and take decision based on causal knowledge. And this is very important for several reasons, but in general, it allows you to reason about the effects of actions that you might take in an environment and how these will produce certain results. So for instance, if we look at this graph, which has been used in the past to analyze the causes of lung cancer, and this specific graph has been taken by the Book of Why, which is a nice introduction to causality, you might want to analyze whether, actually reducing smoking has an effect on lung cancer, or whether there are other aspects that are affecting this probability. So there are a lot of processes and systems in the real world that can be described by causal graph and can decompose in sets of interconnected nodes. And I'm going to give you some examples here. So this causal graph here describes the way in which different variables like error population at different times and soil fumigants affect the crop yield. And in this discussion, I'm going to use dashed edges to represent unobserved confounders, while shaded nodes will represent variables that can be intervened and manipulated. This is only one of the classical examples used in the causality literature. Another example is given by this graph, in which you have different environmental variables that are affecting the level of classification rate for a coral system. And in this case, you see dashed nodes, and this represents variables that are called non-manipulative and are variables that can be intervened on, that can be observed, but that cannot be intervened on. Another example is given by this additional graph that describes the way in which different risk factors affect the level of prostate-specific antigen. So in this case, we have age, we have BMI, we have cancer, and these variables cannot be intervened on. We can only observe them, but we can intervene on the level of statin or aspirin drugs that a patient can receive. So we can identify some common elements in these examples. So we have a system that is described by a causal graph, and I believe you saw before. It's generally, it's a directed acyclic graph or a DAG. We can collect observational data from the nodes that are node hidden, so observed nodes. We can run experiments either in reality or through the construction of a simulator, and each experiment has a cost that depends on the number of variables that we intervene on and the type of nodes we intervene on. So the research goal that we're going to look at is how we can efficiently find a system to extract all of the possible information, especially because experiments are generally very difficult to implement. So looking back at the example that we introduced before, again, the crop yield graph, we might be interested in answering different questions. So we might be interested in learning how the crop yield behaves given different intervention in the system. We might want to select the optimal intervention. Again, optimal level of L-word population or soil fumigants optimizing the crop yield. And we might want to also draw some conclusions about how different causal effects are correlated in the causal graph. So for instance, let's say that in the past you have intervened on soil fumigants and you have observed the corresponding crop yield. How is this correlated with an intervention and an alternative intervention that you might decide to implement in the future? Can we draw some conclusions starting from things that you've seen in the past? So in order to answer this question, we need to do three things. So first of all, we need to perform experiments. we need to integrate observational and observational interventional data. And we might also want to transfer interventional information. And these things will become clearer as we discuss causal Bayesian optimization. So in general, in order to find the optimal configuration, the optimal intervention, we need to frame an optimization problem in terms of causal terms. And I'm going to give you a bit of a very quick background on things about causal models that we need in this approach. So in the following discussion, we're going to consider a causal model, and the causal model is represented by a DAG, so the graph, and a 4-tuple. And in the 4-tuple, we have exogenous variables associated with a specific distribution. We have endogenous variables, and we distinguish between a target variable that we wish to optimize, manipulative variables that we can intervene on, and non-manipulative variables that we cannot intervene on. And we have also a set of functions that are mapping each the parents and the exogenous variable to the node. So for instance, if we look at this XYC graph, that is the classic example of the existence of a confounder, observed confounder. So we have a causal graph on the left, and we have the associated structural equation model on the right, where we have functions mapping exogenous variables and parents to the variable, where each exogenous variable has a specific distribution. So when we speak about an intervention means, implementing an intervention means setting a manipulative variable in a causal graph to a specific value, and is represented by the do operator. And so on the one hand, we have an observed universe. So this is the observational universe. So it's represented by the causal graph and the structural equation model, and we can collect observational data from the system that can be used to estimate the observational distribution, so this joint distribution of x, c, and y. When we intervene, we break the causal relationship between one variable that we set to a specific value, so x, and we substitute the associated equation in the structural equation model with a constant, which is given by the intervention value. So when we observe these post-intervention universe, we collect what we call interventional data that can be used to estimate the interventional distribution, which is denoted by this do operator. And this interventional distribution is actually the object that we are interested in estimating, because it allows us to reason about the effect of actions. So how do we infer this post-intervention universe, this interventional distribution in this post-intervention universe? Well, there are two different ways. Either we actually intervene in the system, we collect interventional data that can be used to estimate this distribution directly, or we observe the system, we collect observational data, and then we use the do calculus to get an approximation of the interventional distribution. So the do calculus refers to a set of algebraic rules that can be used to transform observational quantities to interventional quantities and estimate the interventional distribution, not realizing directly an intervention. And generally, so for example, in this graph, XYC, with the do calculus, we can apply the backdoor adjustment formula to get the interventional distribution as the result of an integral computation. And generally, the do calculus requires you to compute some integrals that are not available in closed form, so you'll need some approximations. Right, so given these causal terms and causal concept, what we want to do in a causal optimization problem is we want to maximize or minimize, I'm going to speak about minimization here now, a causal quantity. So we want to minimize, for example, let's say in the prostate-specific antigen case, the target nodes, so the probability of having cancer, given a specific intervention. So what we want to do is we want to select the intervention variable. These are the XS is the intervention set. So for example, we want to select statin drugs, or we want to select aspirin level to minimize this causal quantity, and we want to select the intervention set and the intervention level. So what level should we set, for example, for statin drug? So with P of X, we give the power set. So these are all the possible intervention that we can perform in a causal graph. And the intervention set, the intervention level is instead considered selected in an interventional domain that is application specific and is generally fixed by the agent. So differently from a global optimization problem, in a causal optimization setting, we want to explore all of the possible intervention and find both the intervention set and the intervention level. In a global optimization problem, generally what you do is you try to optimize a target variable, manipulating all of the possible inputs. So you don't have the problem of selecting the intervention set, but you only have the problem of selecting the intervention level. So if we look at that, these two optimization problem using a causal graph, on the one hand, in causal optimization, you would consider the graph on the left, where you can see that you have complex causal relationship between the variables, and you also have unobserved confounders. You also have no manipulative variables, so you account for the causal relationship. On the right, you see what the corresponding causal graph that would be considered by a global optimization that would break all of the causal relationship between the variables, intervening on all of the nodes. Okay, so one algorithm that is used for global optimization, especially when the target function is unknown, multimodal, expensive to evaluate, or perturbed by noise, is Bayesian optimization. And I believe you have discussed Bayesian optimization in the past talks, but just in case, just as a reminder, in Bayesian optimization, what we do is we construct a surrogate model for the target function, and then we collect function evaluation according to an acquisition function, and then we evaluate the maximum or the minimum at the end, given our observed function values. So when we have exactly the same settings, so when we have a function that is again perturbed by noise, expensive to evaluate, or whose functional form is unknown, but we also have a causal graph, and we want to incorporate the information that we have about the causal relationship between the inputs and the outputs, what we can do is causal Bayesian optimization. So causal Bayesian optimization generalizes Bayesian optimization in settings where we have a causal graph, and the idea is very similar. So what we want is we want to collect interventions, so function evaluation from some causal quantities, and we want to find the optimal among this function evaluation as fast as possible. So the first thing that you might notice, so this is in general the causal optimization problem, and the first thing that you might notice is that exploring a power set of all the possible intervention that we can perform in a graph is very expensive. We can, however, exploit some properties of the causal graph, and I'm not going to go into the details of this, but in general, we can identify some invariances in the interventional space that allow us to reduce the search space. So that instead of like searching in the power set of all the possible intervention, we can consider only some intervention sets that are worth intervening on. So the intuition here is that if I can reach the same result, so the same function value, by intervening on 3 variables instead of 2, by intervening on 2 variables instead of 3, then I should intervene on 2 variables because I'm going to pay a lower cost. So exploiting these, properties, the first thing that we can do is reduce the computational cost of performing this optimization. Right, we are ready to look at causal Bayesian optimization, and we're going to do that by looking at a specific example so that we can visualize the functions that we wish to optimize. So let's look again at the toy example that we looked at before. So we have x, z, and y. Here, all the variables are observed. We don't have no manipulative variables. We don't have an observed confounder, and we have a specific structural equation model associated. And the first thing to notice is that the variable y is independent on x given z. So the intervention on x and z would lead to the same result as an intervention on z. And this is the sort of interventional invariances that I was speaking about before. So we don't need to actually explore x and z, but we can consider either an intervention on x or an intervention on z. And on the right, you see the functions that we're trying to target. So you see on the this plot here, the expected value of y given that we intervene on x. And on the right, you see the expected value of y given we intervene on z. And what we're looking at, where we're looking to find is basically the right level of the intervention on z. So this dashed, the intervention corresponding to this dashed line that represents the minimum, basically the intervention leading to the minimum value of y. So in order to do that, so we have these 2 target functions, and notice that indeed the intervention function related to intervention on both x and z has, it's invariant under different value of x. So it's the x dimension is something we shouldn't consider. And the way we're going to do that is we're going to place a surrogate model, as you do in Bayesian optimization, on each of these target functions. And the circuit model is going to be a Gaussian process, but the prior distribution of this Gaussian process is going to be constructed by exploiting the do calculus that we mentioned before and using the observational data that we have collected from the system. So for each function that we're targeting, so in this case, intervention on X and intervention Z, we're going to have a Gaussian process where the mean function is computed as the estimated expected value from the do calculus, which is this expression in orange. And the kernel function is going to be an RBF kernel, a standard RBF kernel, but the variance of this RBF kernel is going to be inflated to reflect the fact that we might have some uncertainty on the do calculus computation. And this is because of this Monte Carlo evaluation and approximation that we might need to do to compute the do effects. So if we look at this plot, the plot in this slide, you can see that in green, we have observational data. So these are the observational data observed for an intervention on X. Observational data collected from the system regarding X. Then we have interventional data. These are the red dots, and these are previous intervention that we have performed on X, and for which we have observed the associated Y value. In black, you see the true target function for an intervention X that we are targeting. In red, you see the prior GP mean function, and in blue, you see the posterior mean function and the posterior variance. So what you can see here is that the surrogate model is capturing the behavior of the function in areas where we don't observe interventional data. So for instance, between -2 and -1. And this is because do calculus in this area gives us a very good approximation because we have observational data. So through this causal GP prior construction, we have integrated interventional data and observational data, and we have, correctly quantified uncertainty around the causal effects for X. And the same can be said for Z. So once we have constructed these surrogate models, we can see how, these surrogate model differ from what we would get by using a standard GP construction. So if we use a zero mean function and an RBF kernel, the posterior mean function will be given by the blue line in the lower plot. And you can see here that the mean function is just passing through the data points that we observed, but it doesn't capture the behavior of the function in other parts of the input space. So that's why we should use the causal GP prior construction. Now, once we have this surrogate model, we need to collect intervention. How do we select intervention? Well, we can expand the expected improvement acquisition function, which is a standard acquisition function using Bayesian optimization, to select intervention across different sets. So let's say you have to select whether to intervene on X or Z. You have your current best value, which is this white star, and you're going to consider for every set the expected improvement. So how much we expect to get from an alternative intervention on X or Z. And we can find the optimal intervention by maximizing the expected improvement across different sets. So there's a final element to consider, and this is linked to the fact that observing and not intervening might be the optimal thing to do in some example. So we need to decide, before actually deciding on which variable to intervene, we need to decide whether to intervene or observe the system. So causal Bayesian optimization introduces what we call an intervention observation trade-off. So you know that in Bayesian optimization, you have an exploration exploitation trade-off. In a causal Bayesian optimization, you have also an intervention observation trade-off. And the way we address this is through an epsilon greedy criteria, which is inspired by the reinforcement learning literature. So the idea is that at every step, you decide whether to intervene or observe based on an epsilon. And this epsilon is computed looking at how well the observational data are covering the interventional domain. So let's say you're looking for intervention in between -5 and 5 for X and -5 and 20 for Z. And you can see that when you draw observational data, you collect them all in this area that is highlighted by this, is shaded in red. So that means that in order to understand what happens in areas that are not covered by observational data, so for instance, X equal -4 and Z equal -5, we need to intervene. So that's what this epsilon capture, and is proportional, is given by the volume of the convex hull of the observational data with respect to the volume of the interventional space. Okay, so we can summarize the causal Bayesian optimization algorithm in this algorithm. So basically, what we do at every step. So we have a budget of function evaluation as we have in Bayesian optimization, and at every step we decide whether to observe or to intervene. If we observe, we just observe the system. We collect observational data that allows us to estimate the do calculus and so update our prior distribution, which will become progressively more accurate. If we decide to intervene, we decide where to intervene based on the expected improvement. We then intervene in the system, we collect interventional data, and we update the posterior distribution of the function that we have decided to intervene on. So this, this algorithm led to very good results in a variety of real-world and synthetic settings. And I'm just gonna show you one result here because it shed lights on different aspects of causal Bayesian optimization. So if we have a causal graph like the one on the left here, and we are looking for the intervention that optimizes Y, we can run Bayesian optimization, we can run causal Bayesian optimization, and both of them can be run with a standard zero mean RBF kernel or the causal GP prior construction that we have discussed. And so the causal Bayesian optimization is represented by this black and green line. In this case, we just explore different sets, exploiting the interventional invariances that I mentioned before, but it doesn't really matter at this point. You can see how causal Bayesian optimization converges faster than all of the other methods, and especially it reaches the red value. And notice how the red value is actually lower than the orange value. And this is because Bayesian optimization breaks all the causal relationship. It doesn't propagate the causal effects in the system. So the values of Y that it can reach are actually less optimal than what causal Bayesian optimization can reach. So not only causal Bayesian optimization is faster because it selects intervention and intervenes on subsets for paying a lower price, a lower cost, but also Bayesian optimization doesn't get to the same result because of the blocking of causal propagation in the system. So we can, identify some take-home messages from all this. Specifically, many real systems decompose in interconnected nodes, and so doing a causal optimization requires intervening in the system and selecting the manipulative nodes, thereby solving a causal optimization problem. CBO, so causal Bayesian optimization, solves the causal optimization problem using Gaussian processes and improves Bayesian optimization when causal information are available, exploring working intervention and using this GP prior construction that allows to integrate different sources of data. There are various limitations of CBO, but one specific one, it's might lead to an explosion of the number of GPs that we need to actually run this algorithm. So what I told you before is that in order to optimize, to find the optimal intervention, we need to place a different surrogate model on every set that we wish to intervene on. So if the size of the causal graph grows, then the number of GPs that we actually need might be very potentially huge. In addition, suppose that you intervene, let's say on Z, the only Gaussian process, the only surrogate model you're going to update for an intervention on Z is the Gaussian process on Z. So there's no sharing, or you're not efficiently exploring all of the possible information that you collect from the system. So let's look again at the causal graph that we introduced before, X, Z, and Y. And in this case, we said that we have three functions, and we can get rid of one of this, that is the intervention X and Z, because of the invariances. And what you can see is that you have an intervention on X, you have an intervention on Z, and you're placing separate GPs on all of them. But actually, again, this is not efficient because we are not exploiting all of the information, and we want to find a methodology that allow us to transfer interventional information across sets. So it turns out that what we want to do is we want to solve a multitask problem, and you might have seen multitask Gaussian processes in the past. So what we want to learn is we want to learn a set of functions There's a slight change of notation here, but what we want to learn is we want to learn the causal effect, so the intervention function for all of the possible intervention that we can realize. And T of S here is the F of S that we were seeing before, and it's the expected value of Y given that we intervene on XS. So we want to learn this function jointly. We have some observational data obtained from observing the system. We have some interventional data. We want to define a joint prior for all of this function and compute a joint posterior so that we can do some prediction at unseen interventions. So the way we're going to do this is we're going to study the sort of correlation function that exists among these functions. We're going to then, based on this correlation that changes depending on the topology of the graph, we're going to define a joint distribution, and we're going to then compute a posterior distribution. I'm not going to go into the theoretical results of this paper, but you can check there's a theorem if you want to go into the details. It turns out that we can actually express all of the functions that we can define on a causal graph as an integral transformation of some base, what we call a base function. That is this red function here. So once you have identified the base function in a causal graph, you can then do this causal, applied what we call the causal operator, and get all of the remaining functions through this integral operator. So what is this base function? Well, this base function is a function that is again defined on the causal graph and is the expected value of the target node, given that we intervene on the parents and we control for the confounders. So the intuition is that once we have found this function, again, following the conditions of the theorem, then we have some mapping that is represented by this integrating measure, this orange measure, that allow us to get all of the remaining function. So instead of placing independent GP priors on all of the function, we can define consistent prior on all of the function by just placing a distribution on the base function. So this looks very complicated, but if we look back again at the standard, very small toy example that we were looking at before, what this means is that we have a base function, and the base function is the intervention on the parent. So the only parents of Y is Z. So this F of Z is actually the base function. And then the other function, which is the intervention X, can be obtained as an integral transformation of this base function through an integrating measure that captures the relationship between Z and X. So all we are saying is that both the two functions that we wish to optimize in the system can be expressed by only a base function, only one function. Things get a bit more complicated when we look at causal graph where we have multiple parents and confounders, like the graph given here on the right side. So in this case, the base function is given by an intervention on E and D, which are the parents, controlling for the confounders that are A and B. Right, so given that we have a causal operator and all of the functions are obtained as an integral transform, we can place a causal prior, like the one that we defined before, on the base function and then propagate through this causal operator. So that's what we're going to do. We're going to construct a causal GP prior, exploiting the do calculus and therefore the observational data for the base function. And then we can push them through the integral operator. And because of the linearity of the integral operator, what we obtain are GPs for all of the remaining functions with parameters that are determined not only by the data that we have observed for a specific set, but the data that we have observed for all of the remaining sets. So through this construction, we can define a consistent prior, and we can also exploit all of the interventional data that we have selected in the system. So at this point, using this model construction, if you intervene on Z, you not only update the surrogate model on Z, but you also update the surrogate model on all of the remaining functions, so the intervention on X. We still consider a likelihood that is Gaussian, and we can obtain the posterior distribution by standard closed form updates of GP regression. Right, so what we have seen in all of this discussion is that there are different types of data that you can collect from a causal system, and depending on the type of data and the causal graph, you can do different things and come up with different surrogate models that allows you to take decisions. First of all, if you don't have observational data and you don't have interventional data, there's nothing you can do apart from using a mechanistic model. If you only collect observational data, then you can use do calculus to get an approximation of the causal effects and then select action. If instead you have both interventional data and observational data, you can use a surrogate model. And the surrogate model, the form of the surrogate model depends on whether you want to come up with a single task model or a multitask model. If it's a single task model, then you're going to place independent GPs on all of the intervention functions that you're targeting and potentially incorporating observational data through the causal prior construction that we spoke about, getting what we call the GP plus, and that can be used then within causal Bayesian optimization. If instead the causal graph allows you to identify this base function, and I haven't spoken about the conditions for that, but if you can, then you can obtain what we discussed before. So a multitask model that we call DAG-GP because it incorporates the correlation structure coming from the causal graph. And if you incorporate also observational data in the prior construction, you get what we call the DAG-GP plus. Now, let's have a look again for the same function, so the same x, z, and y, at how the DAG-GP model performs. So on the left, you can see a comparison between a single task and a multitask model. In black, you have the true function, so the intervention on x. And in red, you have the interventional data point that we have collected. The green line and the green shaded area gives the multitask model, while the blue represents a single task model. And you can see that the multitask model captures the behavior of the function in areas like, for example, around -2, where there are no interventional data that are collected, nor observational data. And this is because of the information that are coming from alternative interventions. On the right, you can see a comparison between a multitask model with a standard zero-me RBF kernel and a multitask model that uses the causal prior construction. And you can see now in blue the observational data that we have collected for X. The multitask model with the prior construction captures the behavior of the function around -2, where we don't have interventional data, but also around -2 and z and 0, where we have observational data. So it leads to a proper and uncertainty quantification around the causal effects, which is crucial for decision making. Right, so you can decide in the paper that I'm going to mention at the end. We've used this multitask model for just prediction of the function or within active learning. In this case, I'm going to show you the results for when you use this multitask model within causal Bayesian optimization. So you do exactly the same things. You collect data using the causal expected improvement. You use the epsilon gradient to decide whether to observe, but you change the surrogate model to account for the correlation across intervention function. And in exactly the graph that we were seeing before. So the toy model and the more complex causal graph with unobserved confounders. And you can see that the single task, the multitask model with causal prior construction converges and identifies the optimum faster than all of the alternative models. This also for the real example. So here we have used the multitask model within causal Bayesian optimization to select the level of statting and aspirin that are optimally minimizing the process specific antigen. And you can see that using a simulator, because in this case we cannot collect intervention, we cannot do experimentation on patients, and we identify the optimal intervention in around 5 evaluations. Right, so for this second part, what are the take-home messages? Well, we've seen how the DAG-GP model allows you to efficiently learn all of the causal effects in a graph and identify the optimal intervention faster when used within a causal Bayesian optimization framework. The DAG-GP model allows you to capture the non-trivial correlation structure existing among functions that are potentially defined on different input spaces and on different dimensionality, therefore enabling a proper uncertainty quantification, which is crucial for active learning and also causal Bayesian optimization. If you want to read more about these, you can have a look at these 2 papers, and these are my collaborators. Thanks for your attention, and I'm open to questions.
Excellent. Thank you, Virginia, for the exciting talk. We do have a few questions.
Yeah.
So the first question is, In Virginia's talk, the approach towards modeling causal relationship is from the point of view of DAGs. In the previous talk by Andrew and Soren, they used potential outcomes. Is there a relationship between these two framework methods?
Yes, so you can actually map, relatively map one method to the other, and there's a very good paper by Guido Invens that compares the two approach. Generally, they have been developed in different fields. So the potential outcome framework has been generally used in social sciences and economics, and you have some assumptions like the unconfounded assumption that can be mapped to some properties of the causal graph. But there's an ongoing discussion about, the differences between these two methods and whether one should use one or the other. In general, the nice things about the dual calculus is that the DAG approach is that all of your assumptions are summarized in a causal graph that is a visual representation. And so it allows you to better understand whether the assumptions are behind your model. Apart from the backdoor adjustment, which is something that can be mapped to the potential outcome framework and to propensity score matching methods, it has this additional front door adjustment formula that can be used for unobserved confounder, and it's not very clear what is the related approach in the potential outcome framework. But I would suggest you to go through this paper by Guido Invens. I can send the link, and it's a very interesting discussion about the two methods.
Excellent, thank you. Right, so the next question is, could you elaborate on a few more practical examples of causal Bayesian optimization used in practice? Yes,
so if we go back, so this is one practical example. So this is a practical example in which you have, this causal graph has been taken by a Nature paper that is mentioned in the causal Bayesian optimization paper.
I'm sorry, one second, Virginia, your slides are not shared yet. Could you please get the slides to the stream? Hold on. Yes, could we please move from the Slido being shown on the screen to slides? Yeah, excellent. You can continue, Virginia.
Yeah, so this is one real application. This is just one example in which we have a causal graph that has been taken from a Nature paper that is also mentioned in the causal Bayesian optimization paper. And this is a real example in which you cannot perform experimentation in the real world because we are dealing with patients, but we might construct a simulator, we have a structural equation model, and we want to find what is the right things to do, what is the right level of aspirin and static drugs that we give to the patient in order to minimize the process-specific antigen. So this is a specific example. Another example was the real example that I gave at the beginning for net calcification rate. So let me have a look. Let me see if I can find the. Yeah, so this is an example in which we have a lot of different variables that are affecting the calcification rate of a coral system, and it's actually an environmental, problem that is, quite important at the moment. And we have different variables that we can intervene on. Intervening on the system is very expensive, so we want to select very carefully the intervention that we implement, the one that might lead to a minimization of the maximization of the coral reef. And so, you can, incorporate all of your assumption about the system in something like a causal graph, and therefore use this surrogate model for selecting the right things to do. There are a lot of other examples. We have been using these methods, actually a variation of this method for dynamical system, to select the right level of inflation to select, to implement in order to minimize unemployment rate. And there's a paper that is going to come out quite soon. So this is an example in the economy. Every time that you can represent the system with a causal graph and come up with some functional relationships that you can estimate, then you can apply these methods.
I have a follow-up question.
Yeah.
So it sounds very much similar to like which arm to pull in a multi-armed
yes,
bandit.
Absolutely.
I guess here the difference is that there you have like discrete set of arms, and here it's a continuous space you're working on? Correct. Okay.
Exactly. So if all of the variables in your causal graph are actually binary variables, then you fall back to a bounded problem. It's slightly different in the sense that in the bandits, you have a maximization of the cumulative reward generally, while in Bayesian optimization, you're only looking at the optimum of the function. So you're not reasoning in terms of cumulative reward. But you could extend this approach to be non-myopic. So if you think about, Bayesian optimization is only looking at the one step ahead reward, the one that has the highest expected improvement, but you could modify it to look at the cumulative reward, and you will get even closer to a bandit setting.
Excellent, thank you. A few more questions.
Yeah.
Do GPs that model do operator become more computational expensive as compared to regular GPs?
Well, the computational, I'm going to go back to the slide. Okay, so the additional computational cost is in the computation of the prior. And so, well, in general, no, because it's still a GP regression. What you need to compute is the prior, and the prior, depending on the causal graph and depending on the sets that you're looking at, requires you to compute some integrals. And this depends on how you're going to approximate these integrals and whether these integrals are closed form, which is generally not the case. But in general, the computation of the GP is still cubic in the number of observation. And you could, use sparse approximation for GPs here. And you can extend these methods, tackling different dimensions. And the computational cost is definitely one of them.
Mm-hmm. Excellent, thank you. And a few more questions.
Yep.
Let me just mark them. I think the two are similar. So
yeah,
Nicola, I wonder if it's Nicola who also works with Theo, maybe, asks, what can you do if you don't know the graph? Smiley laughing face. And Auxas also asks, what if you don't have a DAG specified? Are the methods to estimate DAG from observational data? So that's a slightly different question.
Very good question, Nicola. Maybe you want to say something about it. I'm joking. So yes, that's a big question. The big question is if you have an unknown graph, and if you have an unknown graph, then you need to account for an uncertainty on the graph. And so there are two different things that you can do. Either you run a causal discovery algorithm before running the algorithm, and you come up with a plausible graph. Problem with that is that from the observational data, you can only select a graph within the Markov equivalence class, and you're not going to come up with a unique one. Or you construct your GP to account for a distribution on the graph. And so account for the uncertainty on it, and maybe collect data that are also useful in understanding what the real graph structure is. And if you use observational data, if I remember correctly, the second question is observational data, you cannot identify the graph uniquely. So you're going to be able to identify graphs that are, that involve the same conditional independence assumption, and you need to do something more to distinguish among them.
Mm-hmm. And maybe as a follow-up to that, what if you do have a DAG partially specified, but you know that there are some unknown confounders on the DAG?
You mean unobserved confounders?
Yeah, unobserved.
Yeah. So you can deal with that in the sense that as long as so there are two different cases. In general, we have run the method with unobserved confounders, and if the causal effects are identifiable, meaning that the do calculus so you can apply the do calculus basically, then your prior construction still holds, and you can use exactly the same method. The problem is when you have unobserved confounders that make some of the causal effects non-identifiable. So in that case, you cannot use the causal prior construction, but you will have to revert back to a standard prior, unless you use some sort of multitask. That in that case, in the multitask, you're going to use the causal prior for some causal effects, the non-causal prior for some causal effects, but you're still going to get some information transfer from observational data because of the multitask nature of the model.
Mm-hmm. Okay, excellent. And I guess the final question would be, where can people maybe find some more like practical examples, or maybe code samples where they could play around with it?
Yes, so the code is actually available for both papers online, and you also have the data that you can play around for the real example that I've mentioned.
Excellent, excellent. So I believe that would be all of the questions. So thank you very much, Virginia. It was excellent.
Thank you for the invitation.
I guess now we are going to go into the break, and we are going a bit early on schedule, so the break is going to be a bit longer. Our next speaker is going to be in, let's see, in approximately 25 minutes. So it's going to be a 25 minutes break from now on. So thank you, everyone, and see you in 25 minutes.
welcome back. I hope that you had a nice break. I'm very happy to present our next speaker, who is Audrunas Gruslys. Today, Audrunas is going to talk about introduction to reinforcement learning. Audrunas works as a senior research scientist in the... So, Audrunas, welcome. The floor is yours.
Hello. It's very nice to virtually meet you in those pandemic circumstances. So in this talk, I would like to talk about an introduction to reinforcement learning. And rather than going into very specific details about different algorithms, I will try to give a fairly broad overview of what the field is about. So in order to talk about reinforcement learning, at first we have to talk about supervised learning. And to start with, I will just reintroduce what artificial neural networks are. So artificial neural networks are connectivist models of computation where activations from previous levels of layers of a neural network are propagated to other layers of a neural network by combining previous activations, multiplying them with weights, summing them together, and applying some sort of a nonlinear function in between. And very similarly, once activations in the second layer are calculated, then activations in the third layer can be calculated. And typically, neural networks may consist of many layers, and the key here are linear operations in between layers and non-linearities. So for example, what is our goal when we are training an artificial neural network? So for example, imagine if our goal was image classification problem, when we wanted to classify images of cats and to distinguish them from images of dogs. So one can take an image, rasterize it, and take every single, split the image into many different pixels, read off image intensities, and treat those intensities as inputs to the first layer of a neural network. Then, during the training process, we would apply a linear operations by mapping inputs in the first layer to the second layer, then apply nonlinearities, then again apply linear operations on nonlinearities, and the neural network would tell what it thinks, whether it's a cat or a dog. And of course, initially, it would guess the answers that are most likely incorrect. So, so the key here during the training process, the key here is to alter all those weights little by little, so that the next time when the same image is produced as an input, the neural network would be more likely to say that, for example, this is a cat, this is the image of a cat. And during the, basically during the training process, every single time we updated those weights, the solution would be more the answer for this particular instance would hopefully be more and more correct. And the goal is, of course, generalization. Once we finish training, when a well-trained neural network should be able to distinguish cats with dogs by taking unseen inputs and correctly attributing labels to them. So for most practical circumstances, this is what the field of supervised learning is about. We have inputs, we want to map them to known outputs. And the answer whether something is right or wrong is typically known instantaneously. Now, reinforcement learning is a slightly different paradigm. So instead of us guessing or classifying whether an image shows a cat or a dog, and we know the answer immediately, now we are in real world, many decisions and rewards for those decisions are delayed. So for example, if someone decides to study computer science at the university, maybe initially one doesn't get an immediate reward for studying computer science. One has to graduate from computer science, find a job and do something interesting, and then gratification and rewards would follow. So very similarly, very often in life, actions have delayed consequences. And initially, whether it is not well known whether a particular action was a good choice or a bad choice. And this makes like reinforcement learning a fairly complicated framework to train, because unlike previously, when a network could be penalized for a bad decision, now it's not clear how good or bad the decision is. Now, to start with, talking about like deep reinforcement learning, one ideally should look into simpler problems first and remember certain tasks from maybe computer science competitions that I believe many of our viewers have encountered previously. So imagine that the goal of the squirrel, which is shown on the screen, is to collect nuts. And a squirrel can go either left or up, but cannot go right or down, making the problem acyclic. And one of the ways to solve this problem is dynamic programming. So dynamic programming is the process when we, for each square, starting from the end of a game, we try to calculate the score, the maximal score obtainable if one starts playing this game from a particular square, and then continuing onwards. So as the last nut is on the top left corner of the screen, like obviously the score is 1. And similarly, when we're considering this square, we see that there is no nut at this particular square. There is one, but it's possible to get one score if we go left. So then we attribute also the score of 1. Now, more interesting things happen if we encounter positions, for example, where a particular where another nut is. So, for example, here we know if we start from this score, we would be able to collect this nut, and then in the future we would be able to still like get one other nut like in the future. And once we fill when we, for example, fill in this particular entry, so we consider what happens if we go left up, and in that case we collect one nut. And what happens if we go left? In that case, like we would be able to collect another nut, and then by going upwards, we would be able to collect the second one. So like this is dynamic programming. Like there's nothing particularly complicated but just by filling a table and using a particular rule, we can calculate what an optimal policy is and how many nuts we would be able to collect. So this is like the standard curriculum in computer science competitions. Now, value iterations are a slightly more interesting problem. So imagine now that instead of only being able to go up and down, we can go anywhere, like up, left, right, and bottom. And as we can close cycles, dynamic programming no longer works. But imagine like the following slightly different problem. Let's suppose that there is a squirrel that wants to catch a nut. It gets -1 score for every move it makes, and there is a slippery slope. So if a squirrel walks along the slope, with a probability of 1, it can slide downwards. With a probability of 0.3, can slide downwards here, and with a probability of 0.1, it can slide downwards like at the other side of the cliff. And the key here is, of course, to find the path that would maximize her reward or minimize like negative rewards. And in this particular case, like we know the dynamics of the world, and we are able to tabulate every single possible position of the world in computer's memory. And we know all transitions. So we know what happens if we go right from a particular square. And in that case, like in those circumstances, we can use value iteration. So value iteration is another algorithm, but unlike dynamic programming, it repeats the same computation for every square, not once, but many, many, many times until convergence. So for example, if we, and for each square, it tries to estimate Q values. And a Q value is the following. Is a number answering the following question. If, let's say, I start from this square, and if I turn right, how many points in expectation I would get? And if one is able to calculate such function for every square in the game, so by always picking the action that would lead to the most amount of points in expectation, what would be maximizing the total reward? And then one would be able to find the path that catches the nut most quickly. So for example, like this is how value iteration would work for this particular square and this particular action to go right. So value iteration would say algorithm would say that when you estimate for a Q value, so for an action value, if we are here and turn right, is 0.1, so the probability of slipping down from a cliff, icy cliff, times the maximal value we can get if we slide down, plus 0.9, so the probability of not sliding down from the cliff, times the maximal value we can get starting from this square, and plus the immediate reward in between those two, in between of those two states. But like in this our example, this is just 0. And if we happen to repeat the same operation many times again for every single square on in the game, like we would be able to maximize the reward. No, okay, fair enough. Like, so why not just use value iteration everywhere? Well, it turns out it has problems because it requires us to know the dynamics of the world precisely. And in some cases, like maybe this is impossible. Like maybe we need to act by trial and error and observe what the dynamics of the world is. So Q-learning is a slightly different algorithm. So instead of relying on us, so it requires sampling experiences from the environment. So a squirrel would learn to reach the nut by trying many different trajectories. We would sample many different trajectories. For every time, every time we were in some state A, we would take, let's say, action like right. We would observe what the next state is empirically. And let's say in this particular example, we slid down with a probability of 0.1. And it would always execute this update rule that basically the new Q value estimate for action right in this particular square is equal to the old one, averaged with a new value of what happens if we slide down, and lambda here is the learning rate. So lambda defines how how quickly we learn from experiences. And the smaller the lambda is, the longer the learning will take, but like the more stable it would be. And of course, like if a squirrel tries many trajectories, every single time it observes, like it visits states, it updates Q values for that state and action in this using this particular formula. After many trials, the squirrel eventually would learn how to reach the nut most quickly. So okay, so far so good. Like, why not use Q-learning all the time? Well, it turns out that it may not be possible for problems in real world may be so large that it may be impossible for us to tabulate every single experience like in our memory, in computer's memory. And it may be impractical to visit every single possible like position. Imagine like if you were walking in Vilnius, like it's hardly possible in a reasonable time to visit every particular position in the city. One may need to generalize. So ideally, what we want to do, we would like the squirrel to be able to try some trajectories. And in dark blue here, I marked squares that are non-visited. And we would like to develop such an algorithm that by visiting some squares and seeing that like, okay, I can slide down here and here it's non-slippery on the top, that somehow the algorithm would generalize and interpolate for the states it had not seen before. By interpolating, we hope that it would be able to solve some practical problems. Well, it kind of makes sense because in life, like people, a person doesn't have to have tried every single street in Vilnius or every particular pavement block of a pavement to be able to generalize that. For example, if I'm walking on the right side of the pavement and on the left side of the pavement, that my arrival time should be approximately the same, or maybe like differ by a very small amount of time. So what we want to do in this particular case with deep Q-learning, instead of having a table that we are filling for every particular position in the game, we would like to train a neural network that would tell us, that would be able to answer the question, at this particular state, if I take action A, what is the expected amount of points I'm going to get in the future? And when I'm acting, I would be acting in the following way. For every particular state, I would evaluate action values for all actions and just pick the one which promises me to give me the best result. And then like an optimal policy would be found. And of course, the question remains how we should train that Q function. So deep Q learning is like an algorithm that is able to train such Q functions. So like we have a huge game, remember, we can't store all states in the table. And we use neural network as a functional approximator. So typically, like deep Q learning, when it is trained on Atari, uses the last 4 frames of a game as an input. Then similarly, like in those examples of cats and dogs, those 4 frames go into a deep Q network, and a deep Q network produces outputs, which would eventually be completely wrong, but as training progresses would become more and more accurate. And the network will try to say, if I'm in this position and turn left, what will happen? If I turn right, what would be the expected reward? And so on and so on and so on. And the algorithm works similarly like I described before. So we play a game and put experiences into replay buffer, like the squirrel which was collecting nuts. Random transitions are sampled from the replay memory, and a Bellman rule is applied. And the Bellman rule is something something not very complicated. What effectively, this fairly complicatedly looking maths tells us that every single time we observe at some transition from one state to another, and we get some reward R, we estimate the new version of the Q of an action value in the old state as the reward plus the maximal Q value in the next state as given by the same neural network, more or less. And of course, in a deep learning terminology, we calculate the delta, we calculate gradients of a gradient of the neural network parameterizing the Q function with respect to all of its parameters. And then we move all of those parameters a little bit towards the direction that would make the prediction more consistent next time. So it's conceptually not very complicated, but in practice it works quite well. And I can show you a few, oops, the video is unavailable. Okay, it's a little bit of a problem. So we will have to use our imagination. Oh, no, never mind. So we will have to use our imagination. So okay, so effectively, the agent is able to learn. The agent is able to learn to play both Breakout, and many other Atari games simultaneously. Okay. Now there are different types of reinforcement learning algorithms. So there are value-based algorithms and policy-based methods. So value-based algorithms are the ones that I've described previously. So it is the algorithm of deep Q learning is one of those value-based algorithms. And the idea here is to train a Q function telling us how much scores we would get in expectation if at state S we take action A and thereafter we follow an optimal policy. However, there are other algorithms like policy gradient-based algorithms. And policy gradient-based algorithms, instead of trying to evaluate action values directly, they try to produce a probability, they try to produce a policy without explicitly evaluating it. So we try to find an optimal policy, we try to produce a neural network that for each state gives a probability with which we should take a particular action. Then, of course, reinforcement learning algorithms are divided into 2 categories based whether we are on policy or whether we are off policy methods. Off policy methods typically allow us to be able to learn an optimal policy without even playing the optimal policy. So it allows us to learn about an optimal policy by looking to the experiences generated by suboptimal policies. However, on policy methods, it can only improve policies that we are playing or we are acting upon. Well, in practice, off policy methods are very important because imagine if one was building some sort of a recommendation system using reinforcement learning, one may want to do some sort of a policy improvement without affecting behavior first. And also, based on whether the algorithms you use planning, there are also different sorts of reinforcement learning algorithms in practice. So the ones which use no explicit planning, so we just estimate action values, as I described previously. the ones which use both, uses both a learned policy and does explicit planning by running Monte Carlo tree search or minimax algorithms. So this is what AlphaGo would do, or many chess programs would do. Or there is another option, which is but the first the planning option typically requires having access to a high quality simulator. And then the last option is, instead of using a simulator, try to learn the dynamics of the environment. And if you don't have access to the real simulator, and use planning on top of it. And like usually, like the last problem is the most complicated problem to be resolved. Now, okay, so there is another like YouTube video that I can try to show. So this time, those are asynchronous methods of this time it is not a Q-learning, but a policy gradient method trying to learn, and not even trying to learn, but playing, I think, like the game of Torx. And you can see like it is able to control that car like fairly well. Now there are also like different training regimes that like I would like to mention. So in real world, we may have to do single episode learning within a single episode. So an example of such problem would be, imagine a delivery robot going onto a street trying to deliver a parcel. Like you cannot like you can only crash so many robots. Then there is the training regime of multiple episodes when we start from the beginning, or each episode, or multiple parallel episodes. And typically most of reinforcement learning research operate in this domain. And even some robotics research operate in this domain when we try to pre-train policies on simulators and then fine-tune policies using real robots in real life. And the last domain, the training regime, is multiple episodes with arbitrary starts and using tree search that I mentioned before. And an example of such regime would be AlphaGo. Alpha is 0 and many discrete optimization tasks when we have simulators available. So in other words, like even when we are talking about reinforcement learning, like there are many different formulations of the problem, and depending on the formulation and practical constraints of the problem, there are different algorithms that would be operating in those domains. Now, another problem that I would like to talk about like is exploration, because exploration is a fundamentally important problem for reinforcement learning. Because before we explore the world, we don't even know what to learn about the world. It is not a supervised learning task when we get served images of cats and dogs, and like we know the domain on which we have to produce estimates. So imagine like we are in Vilnius, we start somewhere close to Vilnius University, and we need to, we want to reach a goal close to Misionierių Gardens. So there are like different ways to accomplish that. Like the first way of trying to find Misionierių Gardens is to just walk randomly. Like choose a random direction, walk until the next intersection, then choose another random direction, and then continue walking like that. And in reinforcement learning, this is called epsilon grid exploration. But one can imagine that one cannot travel particularly far if one is following this strategy, because effectively one is running a Brownian motion. So then like people thought like, is it possible to do somehow better? And like we know from discrete problems and from computer science competitions and classical computer science, that like there are other algorithms that are able to find the decisionation more quickly. So the first algorithm like is a depth first search. So instead of just like executing a Brownian motion, like we would just run a depth first search zigzagging through the streets of Vilnius until we find Misionierių Gardens. Fair enough, but this depth first search is typically not a very effective algorithm, because one may even end up in the situation when one goes to Kaunas first and then like comes back to Vilnius and then finds Misionierių Gardens. So it like arguably like it's a bit suboptimal. But there are other algorithms, and what the other algorithm is breadth first search. So effectively, like the idea would be trying to zigzag, if you were a robot, trying to zigzag streets in some tight pattern by expanding radius gradually until like we find the destination. Those are, of course, like classical search and exploration algorithms, but we can still build some intuition for reinforcement learning. And indeed, like in practice, of course, maybe like it's easy to illustrate the concept on a map of Vilnius, which is nice and two-dimensional. However, in practice, state spaces that we have to deal with are very high-dimensional, because imagine if a robot was exploring Vilnius, who told the robot that X and Y coordinate is the state? Maybe like it's X and Y coordinate and a velocity. The tuple is a state that the robot should take care about, because if, let's say, a robot exceeds the speed or the limit of speed while exploring, it can get busted by the police. So in that case, like even velocity could affect the final outcome of exploration problem. Now, also counting is also very difficult. Like in a discrete problem, when a squirrel is collecting nuts, it's possible to define and understand very easily when we end up in the same state. But what should we do when we are always observe a world that is changing and we can never step exactly in the same river twice? And also we should do something when the world has stochastic dynamics. For example, that can be caused by maybe like wind or by other agents within the environment or the traffic light systems and many, many other problems. So I would like to talk a little bit about typical exploration algorithms used within the area of reinforcement learning. So usually, like most of the algorithms in deep Q learning works in a very simple way. So once in a while, let's say with a probability of 5%, like it just always tries a random action and sees what happens. And actually, it turns out like this is a very ineffective, but like algorithm in terms of data efficiency. But this algorithm works to some extent on many problems that you can try it on. However, there are other arguably more interesting and sophisticated algorithms to be tried for exploration. So like one of the ideas is the following. So if, let's say, we are walking through the streets of Vilnius and we somehow detect that we had been in this place or in approximately the same place multiple times already, maybe we should stop going here and start concentrating on somewhere else. And one such algorithm is called, was produced in the paper called Unifying Count-Based Exploration with Intrinsic Motivation. And the idea is the following. Maybe somehow we have to use a neural network trying to estimate density of states that we had visited. And by density of states, I mean maybe like try to estimate. So the first thing one can think about how this, what should we do when estimating density of states? One may think that maybe like we should have a neural network like just trying to predict the next state, and if what the next state is, if we turn, let's say, right at any given position, and if we mispredict, we should reward ourselves and use the same reinforcement learning framework and just go to places that we cannot predict. Okay, fair enough, like you can try running this algorithm, but the problem is that if you run this algorithm for a very long, you may end up in the situation when an agent just approaches a TV, tunes into a noisy channel and observes all the unpredictability and entropy from the environment. So then people thought, okay, like if just going to places that we cannot predict is not good enough because the agents may be attracted to just simple noise, maybe we should find places and reward ourselves for going to places which were unpredictable, but after observing the transition, they became slightly more predictable. So basically, like if by observing a transition, we were able to understand something better in our past. So imagine the following problem. If we are walking through the city and see the first red car, then we would reward ourselves. Then we observe a second red car and it helps us to better compress the observation of the first red car, so we would reward ourselves again. Maybe like we would reward after seeing the third and the fourth red car, but like after the 10th one, new observations of red cars would not produce any more information about previous observations, and we would stop rewarding ourselves. And effectively, like the paper of Unifying Count-Based Exploration with Intrinsic Motivation tried to do this thing by using generative models and trying to estimate something which we call prediction gains. So instead of rewarding ourselves for observing states hard to predict, we would reward ourselves for states that were maybe hard to predict, but help to predict something in the past. And eventually, once the prediction gain is exhausted, the agent would stop going to that particular place. Now, another like algorithm, which is maybe slightly simpler, is exploration by random network distillation. And actually, it's also like a fairly neat idea, maybe slightly related to the problem that I mentioned before. So if one neural network is initialized randomly, and the second neural network is just being trained to predict what the first neural network would predict for a given observation. And the idea is the following, that if we visit a particular state very, very often, then the second neural network would distill predictions of the first completely randomly initialized neural network, and the discrepancy would become 0, and then the agent should stop being rewarded for reaching that particular position. And also, like, there are slightly more sophisticated algorithms. Like, the problem with a few previous algorithms is the following. So imagine, like, if this particular state, let's say this particular state had a high prediction gain. Reinforcement learning algorithms are usually very, very slow already to converge on stationary rewards. And here we are producing non-stationary rewards. So imagine, like, this particular state has a high prediction gain. So a reinforcement learning algorithm would learn to approach this state until it would start exhausting the prediction gain, and it will no longer be interesting. And it will start giving prediction gain of 0. However, as the reinforcement learning algorithms are slow, it would take a very long time to backpropagate zeros back to the initial position. And for a very long time, the agent would still keep going and keep going and keep going to that position which is already exhausted. And even worse, at some point, the agent would start differing, because as rewards get backpropagated in time very slowly, there would be likely a position where the agent believes that by going right here, it would still get a reward, then would go right, and will figure out very quickly that no, there is no reward to be found, let's go left. And then the value function would be evaluated again and would say, listen, if you go right, like, you will get a reward, and agents would start differing and wasting resources. So, like, this is another fairly cool algorithm that was introduced partially to alleviate this problem. So instead of using a random network distillation that produces a very slow signal of coverage, it also produces and uses an episodic memory and uses an embedding network to somehow embed states. Actually, it doesn't really matter exactly how those states are embedded into some small dimensional space. And the idea is the following. It memorizes all states seen in this episode. And if every single time it observes a new state, it compares state embeddings to previously memorized embeddings from within the same episode. And if a new state was found in this episode, then a positive reward would be given. But if it starts seeing that the agent is wasting time by going back and forth and getting back to the same states within the episode, the rewards would be the rewards would be 0, and effectively multiplicative modulation would produce a 0 reward. So basically, like, this is a method how this is the attempt to increase both intra-episode and intra-episode diversity of states that the agent visits. And to this day, it's one of the most successful algorithms on Atari. And of course, like, the implicit assumption, like, behind this algorithm, like behind many, many other algorithms, is that states are fairly low dimensional, because to this day, we don't know how to explore very high dimensional spaces effectively, and most Atari games at the end of the day are fairly low dimensional. Usually go left or right or forward or backwards, and then continue going in along those directions. So basically, like, I gave an overview of like a few algorithms. And of course, like, there are many families of algorithms that like do other things. So for example, we somehow try to partition spaces and dedicate resources towards exploring within within this subspace of, again, that subspace, that and that subspaces. So maybe, like, the goal is, of course, try to somehow emulate as much breadth first search rather than depth first search as much as we can. And of course, like, a good exploration strategy, like, it also depends on a good representation that we learn, because it is very important, like, for a good strategy to learn that certain areas or certain variability within observations doesn't matter, while some other variability, axis of variability do matter. So like those were like exploration algorithms. Now I will talk about exploration a little bit. Sorry, not exploration, but applications a little bit, like exploration is already covered. So in order to apply real reinforcement learning in real world, typically one has to solve sim to real problem. Reinforcement learning algorithms, and especially deep reinforcement learning algorithms, are very, very, very inefficient. And typically what people do, we train reinforcement learning algorithms on simulators and then try to transfer the experiences into real domains. And I will cover a few applications. So like one of the applications of reinforcement learning algorithm would be learning bandit algorithm. So bandit is the algorithm, bandit is a problem where typically people encounter when dealing with many problems in life. And one of those problems would be A/B testing. So typically what happens for a particular parameterization of possible distributions of rewards when we pull the left hand of a bandit, and a bandit like can also be fought as a slot machine in a casino. And imagine like a casino player wants to determine which slot gives the maximal rewards. And of course, like the casino player initially has some beliefs about those rewards. Tries pulling, like depending on the beliefs, there are different algorithms how in what order like bandit hands should be pulled, and every single time a bandit hand is pulled, a reward is obtained. The reward, this uncertainty about the reward distribution would be shrank. And even about 10 years ago, for every particular parameterization of a problem, whether we believe that rewards come from beta distribution or some other distribution, there was almost a PhD thesis that was dedicated in finding a particular strategy how you should pull those bandit arms until you decide which bandit arm produces the best results. And like in practice, that would be like related to A/B testing. Like you're presenting maybe 2 website designs to customers, but like you want to make as the least amount of customers dissatisfied, and maybe like terminate the experiment as early as you can, like in case if the success is low. And the key in here behind the algorithm called learning to reinforcement learn was the following. So instead of spending a PhD thesis for a particular parameterization of a problem, let's generate a lot of bandit problems. Ask the reinforcement learning agent to pull those hands. And depending after a certain budget of pulls that we can afford, reward the agent whether it knows which hand was the best or which hand was the worst. And then this algorithm is able to learn an optimal pulling strategy for a particular parameterization of a problem reasonably quickly, like without spending a PhD thesis on it. So I personally found this application to be very cool. The second application that was often talked about, like reinforcement learning, can help to reduce data center and cooling costs at Google. And also reinforcement learning can learn to control balloons. And this is a fairly new paper by Google Brain, by Belmer et al., published in Nature. And the idea is the following. Google had the project Loon, where the aim of the balloons was to hover over a particular place and provide connectivity. And depending on, but the balloon can only do 2 things: go up and go down. And depending on where the winds are blowing in different heights in the atmosphere, by going up and down, the balloon can explore winds. And then by choosing optimal winds, it can learn to hover over a particular area, which I think like is 50 kilometers around the base station. And typically, like most of this work was done by just having handcrafted controllers. But it turns out that the reinforcement learning agent was able to beat all of those handcrafted controllers and keep the balloon over the dedicated area with a maximal precision. And of course, like the idea of solving this problem was having a good weather simulator for a particular place, using reinforcement learning to train strategies using deep Q network, this more or less a very similar algorithm to the one that was playing Atari, and to reward the algorithm for whenever it is it keeps the balloon within 50 kilometers from the base station and reward less if it flies further away. And it turns out that the agent that learned on a simulator was able to control real balloons. And the key here behind the behavior of the agent is still the problem of exploration versus exploitation. The agent, to some extent, needs to move around up and down to explore wind directions. So basically it needs to explore, but also it needs to exploit in order by choosing optimal heights so that it would be able to hover over a particular place. The third application of reinforcement learning that is super cool is chip design, because I'm not an expert of chip design, but the way how I understand the problem is that once the logic of a chip is designed, and we know that we have a bunch of components that have to be physically located on a two-dimensional chip somehow, we would like to arrange those parts in a way that total wiring distance would be minimized, because wiring both costs the money, and also wiring introduces latency, wiring produces heat, and it is a very highly non-trivial problem to produce an arrangement of parts on a chip subject to the constraints that the chip designer has. And the idea is, of course, that a neural network was trained by producing a very diverse set of possible chips that have to be placed on a two-dimensional board. The agent was then asked to choose a position of each chip one by one by one by one. And after all the chips were placed, if the configuration was feasible, then a proxy for a reward was evaluated, and the agent was fed into, and the reward was fed back into the reinforcement learning system. And then at the end of the day, the reinforcement learning system was able to generalize to position components of other previously unseen arbitrary sizes. I think this is a very cool application of reinforcement learning yet again. And this is another work, this is not from DeepMind nor Google, this is from OpenAI. And this is an example of reinforcement learning when it was used in robotics. And reinforcement learning algorithms were trained in simulation to do dexterous manipulation of objects. A robot hand was trained to manipulate a cube in its hand. And the experience, as the simulation produces experiences which were diverse enough and algorithms were good enough, the experiences were able to transfer into the real world as well. So I think this is a cool application of reinforcement learning. I personally, the more time I spend, I personally more and more care about applications, and I think that the area of reinforcement learning has a lot to offer. Another application of reinforcement learning is improving machine translation, because typically machine translation models are trained to minimize cross entropy and predict each word at one token or word at a time. So let's say an input is a French sentence, the output is an English sentence. However, once you produce, if you train networks like that, instead of producing the maximally likely or the best outcome, one is producing a typical outcome. And typically, and then there is another problem that by choosing a word which is very likely at position 1 may end up being in a situation where one has to choose between very unlikely words in a position 2. And typically, either in machine translation, people use either greedy search that produces slightly suboptimal results, or beam search that tries to maintain a bunch of beams with possible word positions at every choice. Imagine initially it would be maintaining the option to choose A at this position and C at this position, but after seeing what other likelihoods are for token in position 2, it would be rejecting previously seen position C, and then would continue, all those beams would continue along those two lines. Or it is possible to use a Monte Carlo tree search, an algorithm very similar to the one used in AlphaGo, and to run a tree search to produce for the most likely outcomes. Or ideally, or also not necessarily produce the most likely outcomes, but also produce outcomes that measure some other measure that we are interested in, as opposed to cross entropy that was used to train it. So effectively, like Monte Carlo tree search can be used to consider a whole variation of possible translations and like in a tree-like manner, and then pick the best one. So yeah, I think like I mentioned like most of those things before, and like there is the last topic, which is called multi-agent reinforcement learning. So previously we talked about like the problem of a single player in the initial examples, when everything is seen, like, and way a particular player knows exactly when one is. So this is the setting of Atari, a squirrel connected nuts, and so on. However, like in robotics and many other problems, we don't have MDPs, Markov decision processes, but we have partially observable Markov decision processes. So for example, in robotics, the agent, due to the position of the camera and stochasticity in the environment, may not be able to see where its hand is at any given point. Let's say if my hand was behind my back, like I can no longer see where my fingers are. So an example of such problem would be robotics. Then we have two-player problems, which are fully observable, like chess and Go. And we have two-player problems that are partially observable, and an example would be a two-player poker. Then we have three-player problems, which are fully observable. An example of them would be Risk. And we have problems that are multiplayer problems and partially observable. An example would be multiplayer poker with more than two players. And as a rule of thumb, actually to this day, we as a community, we don't know what to do with three-player problems and beyond. But we have a fairly good understanding how to deal with two-player problems. And the Go is an example of such problem, which is fully observable. And it has two players, and like it was one of the initial achievements of DeepMind that made the company like somewhat famous, I would say. So unlike chess, which has a reasonable numbers of choices for every move, Go has a very, very high number of choices for every move, making running a normal tree search, an exhaustive tree search, not very feasible. And instead of running a tree search, the Go project, it does run a tree search, but it needs to do very aggressive pruning because not all possibilities can be checked. And Go used convolutional neural networks, both for a value function that was trained using reinforcement learning and for policy function as well. And instead of running an exhaustive search, it was using Monte Carlo tree search guided by the policy and value networks. And this allowed to do a very effective pruning of the tree search so that the gameplay would become feasible. And as I mentioned before, like very similar technologies using Monte Carlo tree search, actually these days can be applied in text generation problem and machine translation problems. So basically, like the technology is more practical than just for a single game. And then there are, as I mentioned before, imperfect information games. So for example, imagine like we have two players. Player one has to choose whether to go left and right, and player two cannot observe whether player one chose to go left and right. Unlike in Go and unlike in chess, it is very hard to know for player two how it should best respond, because player one may be bluffing and the optimal strategy may not be a deterministic strategy, but it may be like a stochastic strategy. And to illustrate this the problem of imperfect information, one can like very easily imagine a fog of war that one sees in many computer games. So imagine like if this is the first squirrel that has to make a move, and this is the second squirrel that can see only one step ahead. As long as the first squirrel doesn't make a move which goes into, as long as the first squirrel has to make a move which is either left, up, down, or right, the second squirrel is not able to know where the first squirrel is, and as we are competing for this nut, the second squirrel should be able to handle many different actions of the first squirrel and also bluffing strategies. And in perfect information games, especially when we are zero-sum, we are, instead of we are trying to find Nash equilibria as opposed to a deterministic best response strategy. And like finding Nash equilibria is fairly important. So an example of such domain is StarCraft, and AlphaStar was an algorithm used by DeepMind to learn to play StarCraft. So unlike Go, the problem is very complicated, also much more complicated in some senses because it's partially observable. You can't see what the opponent is doing. Your opponent may be bluffing, and you would have to bluff in order to prevent your opponent from exploiting you. And also, like another project was Capture the Flag, where teams, where neural networks were able to were trained to play the game of Capture the Flag, and which is also very highly partially observable because it's a three-dimensional game and you can only see like what is in front of you. And typically, like it sounds like multi-agent problems may not have like a lot of applications, but it turns out that we have, and applications are in auction design, in energy systems, especially smart grids, when one is trying to find policies that people would respond to in desirable ways, or also like in transport networks. So thank you very much for listening. Like it's been a pleasure presenting to you. I'm looking forward to any questions if you have any.
Thank you, Drunos. You're right on time, and we have a few questions. So let's start with the question from Dmitry.
Okay.
He's asking, are you familiar with intersections between reinforcement learning and causal inference or experimental design? And if you have any pointers regarding these intersections?
No, I actually like I do not like have like so much experience myself like within that intersection, so like I'm not able to answer this question properly. The issue like so like this is my answer, like my apologies.
All right, it's I think okay. We have a few more questions. Another one by Dmitry. Could you potentially elaborate on how reinforcement learning is used in AlphaFold?
I'm actually like okay, like I cannot like answer this question because I'm not so familiar with the work of AlphaFold myself. Like, and to the level that I'm familiar, like I do like I don't want to speculate nor like mislead you by an accident. So like my apologies, like I cannot answer this question as well.
Okay, let's we still have like a few questions, so I think it's okay. Maybe you know you could like Dmitry could ask you the questions on Slack, and
oh yes,
you could answer them on Slack. All right, perfect. Let's move to the next one. Robin is asking, the reward design seems to be very hard and require human expert knowledge in the real world example, like the balloons. What to do if we don't really know how to design the reward?
So like, okay, like to some extent, like we still need to be able to define like what the success is in some ways. Like, because like if you cannot define what the success is, like basically like this is game over. Actually, like there is a stream of research within reinforcement learning, which is called no reward learning. So basically, like the idea is how much can you learn about the environment if you don't know what you're doing? So to some extent, like maybe like those are people on Earth, like people ask philosophical questions, what is the meaning of life and those kinds of things. However, like the third approach, if you have some vague idea of what the reward is, at least you can attribute like +1 to some states and 0 to the others. Like you can maybe like try to evolve like your reward functions, but like generally speaking, like you still must know what you want from your robot, because you don't want the robot to impose your will on you.
All right, yeah, great answer. Yeah, so in all cases, I guess it's important to at least know what you want the agent to do.
Exactly.
Let's move on. Abhirup is asking a question. What are your thoughts on improving the data efficiency of reinforcement learning algorithms? Also, is there a possibility that the use of a specific exploration strategy might bias the agent towards a particular solution?
Okay, answering from the easiest part, yes, the use of a particular exploration strategy would most likely bias the agent to a particular solution in those circumstances when the optimal solution is not found. Because you see, like ideally, if everything works correctly, like the agent is in theory supposed to find an optimal solution. However, there may be some solutions that share the same expected value. So in that case, like, of course, the strategy would bias. And the second thing is, it may not find that optimal strategy. And yes, of course, it would bias, because like a bad exploration strategy may just give rewards of 0. Now, this is the second part of the question. I forgot the first part of the question.
So I'll repeat the first part.
Okay.
What are your thoughts on improving the data efficiency of reinforcement learning algorithms?
I think like it's very important for many domains when you don't have a simulator. So for example, a robot in real world. However, or like a recommender system being updated, or A/B testing, or anything like that done with real people, like with real clients. However, and it is very important to update data efficiency. In my view, in the community, there is a little bit of a blind spot, like at this particular moment, that like people don't care about data efficiency as much maybe as I do. However, there are also some other problems why it really doesn't matter. So an example of that would be a bridge building simulator. Imagine like you want to design an optimal bridge and you know how to simulate a falling bridge. However, while you can simulate the bridge, you don't know how to design a bridge. And in that case, like data efficiency doesn't matter, then exploration is very important, because so like that would be like one of the examples. Or even like in a very general case, like maybe like protein folding problem. Like if we knew how to explore the space, high dimensional space very, very efficiently, like maybe the protein folding problem would be even easier. But like it's also partially an exploration problem.
Yeah, all right, great answer. Let's move to the next question. Do you have any suggestions how to handle non-stationary environments?
Like it depends on an algorithm. Usually on policy algorithms, from my experience, handle non-stationary environments better than off-policy algorithms. So for example, like maybe A3C would have less problems with non-stationary environments than DQN. So like typically like there are tricks, like for example, like bootstrap less often and use the actual return as much as you can, because like every single time you if you bootstrap at every state, you are decaying your now invalid rewards very slowly. If you're using full returns with importance weights without any bootstrapping, then you're not almost suffering from non-stationarity as much. But like, so basically like there are a few other things. However, like maybe there are algorithms in between. Like you can think of like running statistical tests, trying to determine when, let's say, your data in your replay memory becomes irrelevant. But generally speaking, like I don't think that like any very clear answers have been obtained, and typically reinforcement learning operates the best when the rewards are stationary. But this is a very good question. It's a very open problem.
Yeah, and maybe to add a little bit to the answer, yesterday Razwan covered quite a bit on the non-stationary learning in his talk about continual learning. Mm-hmm. So I think it will be worth to check out for the person asking the question. Mm-hmm. Let's move to the next one. So James is asking, what is the most popular / general approach to researching reinforcement learning? Is it more computational, iterative method, or mathematical modeling?
Okay, like it's very hard. Like it's almost a philosophical question. I think like at the moment, most of the work, like due to the compute power that we have, like a lot of the work has shifted towards more experimental methods. Like, however, like typically, like the best methods are actually fairly heavy mathematical as well. Like people. Like you still have to prove that something is an unbiased estimator and has low variance. So both, I would say.
All right. Yeah, thanks. The next one is, Robin is asking how to deal with, POMDP, as you mentioned. Is recurrent networks enough? Sorry, I missed the
Well,
abbreviation.
it is enough in theory, like if you have a single player. But if you have more than 2 players, like algorithms like are very different. In practice, it is not necessarily enough. And like there are other algorithms that are designed for multiple players and partial observability. So for example, like counterfactual regret minimization, like would be able to deal with it arguably better than maybe like Q-learning. Using naively, and there are like versions of very special algorithms that typically were designed for a multi-agent case. However, like recurrent neural networks in theory are enough, but like whether in practice they converge, like it's a separate problem.
All right. Next, Mantas Lukoševičius is asking, is actually like congratulating you. A very nice talk. You mentioned that some kind of simulator of the environment can also be learned, which looks biologically plausible. What about learning a simulation of other agents in the environment?
Oh, so, okay. So it is already like, in a general case, difficult to distinguish what another agent is unless you're told. Because this is the non-stationary part of the environment. And even like learning simulation itself is very tricky. Imagine the following thing. You make tiny mistakes. And imagine like you are trying to squeeze through a door and a bus, but the door is just like too narrow. And like it may make a very big difference, like if you get stuck in the door. And what happens typically with learned environments, unless you learn them very precisely, and when you use planning algorithms like MCTS on top of them, you can try to squeeze through the gaps that are just too narrow because you're launching an adversarial attack on your model. So the point is, you can try learn the behavior of your opponents. By the way, but it is difficult, and many reinforcement learning algorithms designed for multi-agent case do that implicitly, not explicitly, but implicitly, like they reason about like what your opponent could be doing. So, but of course, like there is the distinction whether you want to plan based on it and run a tree search, or whether you just want to read off a value function. So like to some extent, like if you would just want to read off a value function, to some extent, like StarCraft would be doing that, but would be doing that implicitly.
Right. Yeah. Thanks for your answer. I think that's all the time that we have today.
Thank you very much.
For everybody else, if you still have questions for Audrunas, please post them on Slack. And Audrunas, would be really great if you could join our Eastern European Machine Learning Slack and check out or answer a few questions.
Okay. Thank you. It's been a pleasure. Have a good day.
Yeah, thank you. And we are going into a break. We'll see you back in 8 minutes. And then we'll have another speaker, Carolina, who is going to talk about the progress towards understanding generalization in deep learning. So see you in 8 minutes. Welcome back. I really hope that you had a refreshing break. I'm super happy to announce that our next speaker is Karolina Džiugaitė, who is going to do a talk called Progress Towards Understanding Generalization in Deep Learning. Karolina is a lead research scientist at Element AI. Her research combines theoretical and empirical approaches to understanding deep learning with a focus on generalization, optimization, and network compression. So Karolina, welcome, and the floor is yours.
Thank you. Thank you for the introduction and for the invitation to give a talk here. So I'll be presenting joint work with a number of my colleagues listed below. The central question of my research is, why does deep learning work? And in this talk in particular, I'll be focusing on why does deep learning generalize? There are a lot of exotic notions of generalization, out of distribution generalization, few-shot learning, transfer learning, and so on. In this talk, I'll be focusing on arguably the simplest notion of generalization in distribution generalization. So why focus on the simplest notion? Well, there is as yet no satisfying theory explaining why over-parameterized neural networks trained by variants of stochastic gradient descent generalize from training data to test data on standard benchmarks. And of course, without a solid foundation, we have little chance of understanding and taming more complex notions of generalization, such as out of distribution. This gap between practice and understanding is a growing liability as we start integrating deep learning into healthcare, self-driving cars, and other high-stake applications. In this talk, I'll describe recent progress past barriers. So let me start with a backstory. A few years back, Zhang et al. Published a paper on understanding deep learning requires rethinking generalization. And now it's a well-known paper, a well-cited paper, so I'm sure that a fraction of you know it, where they show that networks trained on standard data sets could achieve both zero training error and good test error without any explicit regularization. They also observed that networks had a very large capacity, so they could memorize random labeled data sets. This is problematic for various theories, such as VC Rademacher based for when bounding the error of 0-1 loss classes. And the bounds that you obtain on generalization error, which is the difference between training and test error, are vacuous. So at the time, the reaction from experts was that what was obviously missing from Zhang et al.'s story was margin and norm-based capacity control. And indeed, a few years before that, or 1 or 2 years before, Nature et al. Also had very similar observations showing that SGD's generalization error was not affected by increasing network size or lack of regularization. This motivated the authors to propose what they called implicit regularization as explanation. So the likely explanation was that despite there being no explicit regularization during training with stochastic gradient descent, SGD has some kind of implicit regularization, perhaps controlling the norms or the weights, maximizing the margin, or whatever else. And this is in line with work by Bartlett from 20 years back, where Bartlett proved generalization guarantees for neural networks in terms of the L2 norm of the weights. So he showed that no matter how large your network is, maybe even infinite, for as long as you have a small norm, you'll have a good generalization error. Bartlett looked like sigmoid networks, and L2 norm made sense in that setting. But when it comes to relay networks, they're invariant to various rescaling. So for example, you can upscale one layer weights, downscale another layer weights without changing the L2 norm. So Nature et al. Introduced a path norm based Rademacher bound on generalization error, which was actually custom built for relay networks. It was scale invariant. So what these bounds say is that, again, no matter how large your network is, how deep, how wide, if you have a small norm, after rebalancing the weights perhaps, and you have a large margin, then you'll have a small generalization error. Again, the bound on the test error, the difference between test and train will be small. What hasn't really been appreciated or had not been appreciated at the time was the role of empirical evaluation. So margins, norms, they all are data dependent. And so the question of whether these bounds explain generalization in deep learning is somewhat an empirical question. And that's exactly what I did a few years back. So I went ahead and trained a small neural network on MNIST dataset, so handwritten digit dataset. And I found that, sorry, whoops, let me go back by a couple of slides. And I found that the path norm that the bound depends on grows during training. So the x-axis here is training epochs, training iterations, I believe, and the path norm is plotted on the y-axis. Now, this wouldn't be an issue since the generalization is bounded by the path norm divided by the norm, divided by the margin. And for as long as the margin grows, it's all fine, and it does grow throughout training. But note that the path norm is plotted on the log scale, and it grows much faster than the margin, overall leading to a vacuous bound, which is this green line here. And the orange and blue lines are the test and train errors. Now, one may ask, what if I add explicit regularization, minimizing the path norms? So perhaps, SGD's implicit regularization is not sufficient, and I need to explicitly regularize for the path norms. And if you do explicit regularization, and here are the middle and right columns, you'll see that the path norm does slow down, does grow as much. It plateaus at a smaller value. But unfortunately, the margin as seen from the bottom row plots also plateaus at a smaller value, and still leading to vacuous or pretty loose bounds. So only when you have very high regularization of the path norms, as seen in this right top plot, you'll have a non-vacuous bound. So the bound on your test error will be, let's say, 80% in this case. But note that the train and test errors are now 30%. And this is a binary classification problem on a very easy data set, MNIST data set. So you kind of get a useless classifier at the end. And in these particular experiments, I showed that the bounds are vacuous. So the bound on a quantity that's error between 0 and 1 is above 1, meaning that the bound is vacuous. But these experiments have been extended since, and by Nagarajan and Clocher, and they showed that even the dependencies on the, let's say, on the number of data points, the width of the network, they're off. So here I showed that empirically, the norms are not small enough relative to the margin to explain generalization in deep learning. And if we want to explain generalization in deep learning, we can't just find, say that some X explains generalization, such as small norms and large margins, but we also need to show that we can find X. So if we train a neural network with stochastic gradient descent, we actually find X. We find norms that are small enough and margins that are large enough that lead to generalization. And this green part here is missing from the margin bounds. So what structure can we connect to generalization, both theoretically and empirically? If not margin norm, what is sufficient? So a few years back, there were a few papers published showing that wide minima or flat minima generalized. And this actually connects to some older ideas. And the idea is the following. So imagine that, or the idea that we had was the following. So imagine here's your optimization surface. And SGD ends up, the end trajectory is somewhere here, landing in this minima region. If you perturb the weights, you'll actually, if you perturb within this region, you'll actually not incur too much extra error, training error. So the SGD solution is, the flatness means that the SGD solution is invariant to perturbations up to some scale. And this is exactly what we take advantage of using fact-based bounds. And here's some older related work kind of on somewhat related ideas from 1990s and early 2000s, if you're interested to check them out further. So let me define fact-based, which will allow us to formally connect flatness to generalization. So assume that the loss is bounded and the nature chooses some data distribution D. We get to choose a distribution P on the weights, the so-called prior. So here's our weight space, and we choose, let's say, a Gaussian centered somewhere in the weight space. Then the nature gives us an ID sample training set S. And now we get to know the empirical risk surface over which we'll be doing our optimization. So in this example here, as seen in these figures on the right, we see that there are two minima. One is a flat minima, another one is a sharper minima, but perhaps achieving a slightly smaller error, empirical error. then what fact-based bounds tell us is that with high probability for any posterior classifier Q, so I can put any distribution on the weights, and the generalization error of this posterior classifier Q will be bounded in terms of the KL divergence between Q, my posterior classifier, and P, the classifier that I placed, that I chose before seeing the actual training data. So again, in this case, we can choose two Qs. Let's say we choose a Q here, which is centered at the flat minima region. And the variance is chosen, let's say, not to incur too much training error, right? Because if we perturbed it quite a lot, our error would be going up. Training error would be going up. And we can choose Q prime centered at the sharp minima region, but the variance has to be much smaller, of course, again, to balance the empirical risk. What fact-based bound tells us is that the bound on the generalization error of Q will be smaller than the bound on the generalization error of Q prime, because the KL divergence between Q and P will be smaller than between Q prime and P, due to Q prime having very constrained variance. So in our work, in our 2017 paper, we used fact-based and we study classifiers Q that are Gaussians centered at the weights found by stochastic gradient descent. And we choose a prior P, which is also Gaussian centered at the initialization, so where SGD's optimization is being started from. And we actually, by combining fact-based with explicit optimization of these variances to minimize the bound, so with non-convex bound optimization, we obtained first non-vacuous bounds for over-parameterized deep neural networks, which was, of course, an achievement. And unlike contemporaneous work on bounds, we focused on the empirical evaluation from the very start, which I think is very important when it comes to trying to build bounds guarantees that explain generalization in deep learning. But there are a few weaknesses. The bounds are still numerically too loose to explain observed generalization. So for example, in that case, we had binary MNIST data set where the test error was, let's say, 3% or so, and the bound was on the range of like 14 to 17%. So it's quite loose. And another issue is that the bounds hold only for perturbed classifiers, not the original one, right? So we didn't just look at generalization error, all the weights found by stochastic gradient descent, but we actually had to perturb and fit a Gaussian around in order to use fact-based and obtain a bound at all. And the third issue is that the bounds don't scale correctly. So as we increase the network depth, I believe, we found that the bounds got worse. And in practice, the generalization error or the test error actually decreases as you increase the network size. And this issue arises due to the particular choices of the prior and posterior. We chose them to be Gaussian, and the prior was centered at initialization. So the bounds depend on the distance of the weights to initialization due to the choice of the prior. So what are we missing? What are the barriers to explaining generalization? Well, I think there are three barriers. One is statistical, another one is computational and analytical. So generalization error may rely on favorable properties of the data distribution, but of course, real world data distributions are unknown. And if we center the prior at initialization, we don't take advantage of the nice properties of the data distribution potentially. Another barrier is computational. Generalization may rely on quantities that are known but are hard to compute. So for example, if we could write down the distribution that SGD samples from, perhaps we could do much better. And the analytical barrier is that generalization may happen in ways that our current mathematical tools cannot capture. So perhaps we don't even have the right theories to explain generalization in deep learning. So let me talk a little bit about overcoming statistical barriers and fact-based by data dependency. Tight fact-based bounds depend on the data distribution. So consider a data-dependent posterior Q, so some randomized classifier on, let's say, the weights of the neural network. This is the fact-based bound that I had in the previous slides, bounding the generalization error of this Q in terms of the KL divergence between Q and P. Now, it is well known that the prior minimizing the KL bound, so the KL term in expectation, is actually a distribution-dependent prior. So the optimal, the oracle P star, equals the expected posterior Q. A prior is actually a prediction problem. You're trying to predict where our Q will land given the data. And the unknown data distribution is a statistical barrier. So PAC-Bayes has this fundamental tension that the prior P can depend on the data distribution, but it cannot depend on the sample. But of course, our only handle on the unknown data distribution D is through the training data, right? That's all the access that we have. We don't have the data distribution. But as we show in our recent work is that in fact, or just actually to step back, one is actually wrong. So the prior P can depend on the sample. And we've shown this in the past and a few years back using differential privacy. So for example, the prior is learned on the training data, but in a differentially private way, meaning that we don't leak too much information about any individual data point from the training set, then we can actually get a valid bound that's where P, the prior P, is actually sample dependent. And more recently, we show that the optimal P star can actually be also data dependent. So even if you know the data distribution, the optimal prior may be a data dependent one, which is this P star on the bottom, where P star equals the expected posterior, but conditioned on some of the training data. So S prime is a subset of the training set. And this is the P star that was believed to be optimal in the past. So actually we construct an example where using some of the training data, in addition to the knowledge of the data distribution, we can improve our bound, and it can make a difference between a vacuous and non-vacuous bound. So let me just give you a little bit more intuition on this. So let's assume that we train, here's our initialization at the plus sign, and our SGD trajectory. We train on all of the data, we find a classifier here, maybe we fit a Gaussian here to use PAC-Bayes bounds. If we don't have knowledge of the training data or data distribution, we may center a prior at initialization. So this is the red illustration here. If we now instead allow the prior to access a few of the training points that the blue curve, so our original run, has access to in the first few iterations of training, then actually we can totally match the first few iterations of training and let the prior train on the small subset of the data. We may find a prior that we can center somewhere here, which is a lot closer, of course. And since we are, these are Gaussians, and PAC-Bayes bound depends on the Kill divergence between the two Gaussians. If we choose invariances, it will only depend on the L2 distance. So we really care about this, minimizing this distance in this case. If we allow the prior to depend on more of the data, we'll be even closer. More of the data will be even closer, almost recover our posterior. Now, of course, let me just go back a few slides. Of course, note that the generalization error of Q is bounded in terms of the Kill divergence, which is now decreasing the more and more we couple the prior to the posterior. But we are dividing by M, which is the number of training points that the posterior got to see, but not the prior. So our M will be decreasing the more coupling we do. So there's, of course, this trade-off between how much data you use and how much Kill term can be improved. But I think you kind of get an idea how, especially in the cases where you have initial large learning rates and maybe they're decreasing later, it may be important to get the prior access to those first few data points of the posterior sees in order to, potentially break the symmetries and kind of see better where the posterior will land, predict better where the posterior will land. So up to this point, we considered Gaussian perturbations of the SGD learned predictors, which allowed us to capture the role of flat minimum generalization. And in the next part of the talk, I'll consider Gaussian perturbations at every gradient step instead of just at the end, which will allow us to capture the role of mini-batch gradient covariance in generalization. I'll pause just for a second in case there are any questions on the first part of the talk. Okay, I'll move on and I can answer questions at the end. So we'll consider perturbations, as I mentioned, every gradient step. So to every update of WT, which are the weights of time t, will be not only will be taking a gradient step where eta is the learning rate and f is our training objective, but it will also add this noise term where epsilon is sampled from a Gaussian. Eta here, as I said, is a learning rate, and beta is called the inverse temperature parameter. Now, for various different versions of like eta beta, this can be referred to as smoothed SGD or various private versions of SGD. I'll just, for simplicity, really, I'll be talking about stochastic gradient longevity dynamics, which corresponds to particular choices of eta and beta, the particular decays. So this additional noise term makes SGLD much easier to analyze compared to stochastic gradient descent. And the inverse temperature parameter that appears here in the noise term, it trades off exploration versus optimization. So if you look at this one-dimensional visualization on the right and start our stochastic SGLD run at the cross, if we run, let's say, just gradient descent, we'll go to this minima here, the closest one. If we run SGLD, the enough noise will actually end up sampling. So it will be, due to the noise term, perhaps we'll be hopping over this minima, sampling a little bit here, maybe going back to sample a little bit here. So there are two views that one can have of SGLD. One is that it samples from a Gibbs distribution with density proportional to exponentiated and rescaled empirical risk or some other objective that we are optimizing. But this happens only under unrealistic assumptions if you run it for a crazy amount of time and so on. Another view is that it optimizes, and the resulting weights that you learned after optimizing with SGLD do not carry too much information about the training data S. Now, what I'll be asking in the second part of this talk is, does this latter view explain generalization of SGLD? And we'll be using information theoretic bounds to do so. Let S denote the training data, sampled ID from the data distribution D, and W the learned weights that are the output of running our algorithm, in this case SGLD, on the training set S with some additional randomness U, such as mid-batch order or the Gaussian noise term that we are adding every iteration. Then the expected generalization here is defined as, for a particular predictor parameterized by W, is defined as this expected difference between risk and empirical risk. So in other words, really between test error and train error. So assume that the loss is bounded, then Zhon-Roginski showed that expected generalization error, absolute value that is bounded by this mutual information term between the weights at the end of training and your training set S divided by the size of the training set. So we'll be using this information theoretic bound to try to capture kind of the information leaked by the weights about the data set, and we'll be asking, does this theorem explain generalization of SGLD? Again, we run into two barriers. One is statistical barrier. So the mutual information term depends on the unknown data distribution D. And another barrier is computational. Even if the data distribution were known, the mutual information term is actually intractable because it's hard to, again, as I mentioned a few slides back, to write down the distribution that SGD or SGLD samples from. So let me start by addressing the computational barrier. Even if the data distribution D were known, the mutual information term is intractable. So let ST denote mid-batch at time T. So some subset of our full training set S. Pense, Jung, and Low in their 2018 paper, they observed that the chain rule on mutual information implies the following. The mutual information between the data and the weights at the end of training is bounded, can be bounded in terms of the mutual information between the data and the whole trajectory from the beginning until the end, which in turn can be decomposed into these stepwise mutual informations, where we sum over training time and compute the mutual information between at time T between the mini-batch, ST minus 1, and the weights conditioned on the trajectory prior to that point. So in words, the information leaked about the data by the final weights at the end of training is less than the information leaked about the mini-batch at step time T, summed over step times, different training steps. So the next hurdle is that even this one-step mutual information, where we only want to compute the mutual information of the next step given the trajectory, is unknown and also intractable. So again, we run into statistical and computational barriers. So to address this, I'll be using the following insights. This one-step mutual information is optimal expected loss in the following prediction game. So consider a game where you observe the trajectory up to time t. So observe all the W0, W1 up to WT. And your goal is to estimate the distribution Q on the next step, on the next weights. So the distribution on WT plus 1, conditioned on where I am right now and all the past iterates and my mini-batch at time t. So this Q has access to the mini-batch. But of course, I don't have access to the mini-batch. I only have access to the past trajectory. So I need to make a prediction, some distribution P that will only depend on the past iterates rather than ST as well. I'll be paying a loss, which is a KL divergence between Q and P. And actually, as mentioned in the pack-based part, my optimal P star, minimizing the KL term in expectation, is the expected posterior Q. And then the expected loss, so expected KL divergence, given this optimal strategy, for this optimal strategy, is exactly actually my one-step mutual information term. So this one-step mutual information is the expected loss in my prediction game. Now, of course, P star will depend on the unknown data distribution. We don't have access to it. But of course, note that every prediction scheme P that is not optimal potentially yields an upper bound on mutual information. So for any P that I choose, the expected KL divergence between Q and P will be upper bounding the mutual information term, which can be obtained using P star. So stochastic gradient longitudinal dynamics adds this Gaussian noise term, which makes Q take a very nice form. Since I have access to WT and ST, I know exactly the mean of my Gaussian, which is of course just the update of WT minus the gradient. And I know the variance term because I know the variance term of this Gaussian, right? So Q, it takes a very nice form, just a simple Gaussian. But of course, it depends on ST. Going back to Penzias-Jog law analysis, where they bounded the mutual information term in terms of this stepwise mutual information, they play the following game. Again, they observe the trajectory at time t. They want to estimate the same posterior Q, as I mentioned previously. And their prediction, the prediction that they choose to make, is a Gaussian, which is just centered at my current weights, but of course with the same variance because I have access to the variance. So since they do not have access to ST, they just predict the current location. Then they'll be paying a loss, which is the KL divergence between Q and P. Since both are Gaussian with the same variance, it will only be the difference, the norm of the difference between their means, which is just the size of the gradient, which can be bounded in terms of the Lipschitz constants. And the bound that they get in the end on the expected generalization error depends on this kind of sum of our training steps of learning grade times inverse temperature parameter times the Lipschitz constant. But here's the following limitation of these bounds. We must predict the next weights given where we are right now. So we must predict WT plus 1 given WT and everything prior to that. But we have no access to this data. How we solve it in our NURBS paper is using conditional mutual information, where we condition on all but one data point. So now the prediction game becomes a little easier. Not only we observe the trajectory up to time t, but also we observed all but one but the J data point, which is random. And we want to estimate still the same posterior Q, but now we can make the following prediction. We can make a prediction P, which equals to Q if our mini batch is contained in the sample that we got to observe, right? Or we can make a prediction P, which is a Gaussian, where we take a gradient update only on the data, again, that we have access to in this mini batch. And we'll not be paying no loss at all if we happen to have a mini batch that we have access to. And if we don't, we'll be pink, again, is just the KL divergence between these two Gaussians, Q and this form of P. And will be pink cost, which is the norm or the difference between the two gradients, where one gradient is taken on all the mini-batch data, and another gradient is taken on the mini-batch, excluding the JAVE data point that we don't have access to. We refer to this term as gradient incoherence. So let's look empirically, again, how these terms behave. The blue line is the size of the gradient, and the red line is this incoherence term that I introduced in the previous slide. And we see that these are 3 different plots, so 3 different data sets: MNIST, Fashion MNIST, and CFAR10. On the x-axis, we have training epochs, and on the y-axis is just the size of these quantities. And first of all, one thing to note is that this gradient incoherence term is orders of magnitude smaller than the size of the gradient itself. On MNIST and Fashion MNIST, we also see that it vanishes with training time, but unfortunately does not vanish with training time for CFAR10. If we evaluate the actual bound for a couple of different step sizes, the bounds by Moetal that depend on the size of the gradient are the top 2, and ours are the bottom 2 that depend on this incoherence term. And we see that the Moetal bounds become vacuous within the first few epochs of training because the gradient norms are not vanishing. But since the incoherence term is vanishing, our bounds grow much slower and plateau faster. But of course, they're still, still large. And as I mentioned, there was an issue with CFAR10 that that gradient incoherence term actually did not vanish. So the limitation of this work is that we actually have no control over the missing data point. We are missing the random JAVE data point, and we have no control over it. Here is a solution that we proposed in our last year's NIRPS paper. So assume that the training set is one of the following 2 sets, S prime or S double prime, where S prime and S double prime differ by only a single data point. We'll be conditioning on the union of these sets, which we call the super sample. And this is following the work by Stankins and Continue from last year on conditional mutual information, which I encourage you to check out if you're interested. So we observe not only the trajectory, again, up to time t, just like we did before, but we also get to observe the super sample, S prime and S double prime. We want to estimate, again, the same Q. Now note that in these slides, I'll be talking about full batch gradient descent. So Q will be, the gradient will be taken on all the training data S. And our prediction P will be the following. So we'll be with probability theta, we'll have a Gaussian that's centered depending on the gradient taken on S prime, and with 1 minus theta, a Gaussian where the gradient is taken on S double prime. So if, for example, at initialization, we have no clue which of the S prime or S double prime is our training set, we can choose theta to be a half with equal probability. We assign equal probability to both of these potential training sets, and we predict B with theta equals a half. But don't forget that we also get to observe the past iterates W0 to WT, which provides evidence which of S prime and S double prime are actually our training sets. So formally, we actually have a binary hypothesis test, and theta, this weighting here, is chosen based on conditional distribution of missing data points identity. So if we train for a while, we have a trajectory now, that trajectory will be leaking information on which of the S prime or S double prime is the actual training set, and we can start doing much better and make a better choice, better estimate of Q, incurring a smaller cost and smaller mutual information. Again, let's look empirically, and on the x-axis, once again, we see the training epochs, so this is full batch, and the red line is bound depending on the norms of the gradient. The green line is our incoherence term, which for MNIST, we see that it's, it slows down, doesn't go as fast. For CFAR, it grows and explodes, essentially. Actually, sorry, this is the actual bound, not the incoherence terms and so on. And the blue is the new bound that takes into account the previous trajectory and is built on the work on conditional mutual information. And we see that it makes a huge difference for CFAR. Initially, we incur a large cost when the trajectory doesn't leak too much information about the training set, but eventually the bound plateaus and actually stops growing because we essentially learned everything about the data set, and we incur zero cost essentially. So what we've seen is that we can exploit flatness by adding noise to the final weights. So that was a pack-based initial part of the talk. And we can exploit gradient coherence by perturbing iterates with noise. That was the GLD analysis. We can also use data-dependent priors in both cases to reduce impact of the initial unstable optimization and not knowing the data distribution. And we can use conditional mutual information to reduce impact of measuring information leaked by an entire optimization trajectory. But here's the important caveat. The bounded generalization error of perturbations of stochastic gradient descent, which is of course not the same as obtaining bounds on learned weights directly, right? So we perturbed at the end or perturbed every step, but didn't look at the predictor we learned directly. How can we bridge this gap? So let W hat be the weights learned by stochastic gradient descent, and let V tilde be a perturbed weight distribution. So some kind of surrogate classifier. So what we've done in the work that I described before is we looked at the risk of this surrogate classifier V tilde, which can be trivially decomposed just by adding and subtracting terms in terms of the empirical risk of W tilde plus the generalization error of W tilde, which can be bounded, again, kind of standard approach, uniform convergence approach, bounded in terms of the empirical risk of W tilde plus the worst case generalization error over all surrogate classifiers belonging to some surrogate classifier class. Okay, so this is just a standard uniform convergence approach. A direct approach via uniform convergence would be bounding the risk of W hat. So again, we can bound the risk of W hat in terms of the empirical risk of W hat, plus the worst case of generalization error of all classifiers W belonging to some class, some hypothesis space H, where that W hat belongs to. And here's how we can relate W tilde to W hat. So indirect surrogate approach by uniform convergence of surrogate class yields the following. The risk of our original classifier can be bounded in terms of the empirical risk of our surrogate classifier plus the worst case generalization error in the surrogate class that W tilde belongs to, and the difference between our surrogate and original classifier. Okay, so their risks. And perhaps we can obtain some further bound on this difference in terms of the risks. Okay, so we can relate the original classifier W hat to V tilde, the surrogate classifier, perhaps a perturbed version that we've been studying up till now. So is it worth the trouble to go through the surrogate analysis instead of directly bounding the generalization error of W hat and considering a hypothesis class that W hat belongs to? Empirically, no direct approach on bounding generalization of W hat actually gives numerically non-Nyquist bounds. But in fact, there are further barriers, as noticed by Nagarajan and Coulter a couple of years back, an analytical barrier. So a couple of years ago, they got, I believe, like the best NURBS paper award for their work on uniform convergence, may be unable to explain generalization in deep learning. They observed that in norm-based bounds, so such as the ones I described very early in the talk, the norm terms grow faster than square root of n. And note that all the bounds kind of have the complexity term divided by square root of the data points. Hence, the norm-based bounds scale incorrectly with the number of data. So, as we add more data, the complexity term will go too fast, still yielding non-Nyquist bounds. And in their work, they gave a toy examples where SGD learns a good classifier, so the one that actually has good risk, but nonetheless does not belong to a class with uniformly small generalization error. So if you took this uniform convergence approach that I described in the previous slide, bounding the generalization error of in terms of the word generalization error in the class, you will not be able to actually obtain such bounds. So hence standard uniform convergence arguments may fail to explain deep learning. So in fact, they show that directly bounding the generalization error of W hat using uniform convergence in deep learning may not work. And such a surrogate analysis that we propose might actually be necessary. So in our ICML paper last year, we proposed a surrogate analysis where we show just a really simple equation and a definition of a decomposition of the risks, but it's actually insightful and useful to think about generalization error in deep learning for surrogates. So for any surrogate hypothesis V tilde, the difference between risk and empirical risk, so the generalization error, the expected generalization error of W hat equals, so now I'll just be really adding and subtracting the risk and empirical terms of W tilde, but I'll be grouping it into 3 terms. The first one is the risk difference between our original classifier and the surrogate. The second term is the generalization error of W tilde, which we can bound uniformly over the class that W tilde belongs to. And the third term is the empirical risk difference between W tilde and our original classifier W hat. So the generalization error of SGD can be broken down into 3 parts: the error from approximation by the surrogate, and the generalization error of the surrogate, and we can bound this uniformly over a surrogate class, so this orange term. So our approach is to relate the generalization error of SGD to the generalization error of a better behaving surrogate classifier. So in particular, the ones I described earlier, where we perturb the classifiers found by stochastic gradient descent at the end of training, or we perturb every gradient step. So the toy example presented by Nagaraj and Coulter admits a surrogate analysis actually via uniform convergence. And we further, using the surrogate analysis, we further show that for those familiar with Bartlett, Long, Lugosi, Siegler work published in 2019, we show that bias variance analysis of over-parameterized linear regression that appears in their paper can actually be seen as a surrogate decomposition and can be made uniform. We also show that surrogates can be defined by probabilistic conditioning in order to ensure risk difference is 0 in expectation. So this first term, if you define the surrogate via conditioning, totally vanishes, and you only need to deal with the orange term and the last term here. So this is, I know, a little fast and maybe not too easy to understand if you don't have the background, but all this appears in our 2020 last year's ICML paper. And if you're interested in kind of uniform convergence approaches and generally kind of getting past the barriers of understanding generalization deep learning, I again encourage you to check out this reference, or you can email me if you have any questions. So far we've discussed generalization bounds for 2 classes of surrogates, right? Gaussian perturbations of the weights at convergence and Gaussian perturbations of the weights at every time step t. Can we actually control, so we bounded the generalization error of the surrogate, right? But if you recall, there are other terms, such as the risk difference between your original classifier and the surrogate. So can we control the risk difference term to get a surrogate decomposition? So far, an empirical observation is the following, that all proposals to de-randomize pack-based bounds, so to connect the randomized versions to non-randomized versions, produce vacuous bounds. And based on Nagaraj and Coulter work, one may argue that perhaps these arguments trying to do randomized pack-based bounds are too uniform. But again, I won't go into this into too much detail. So what structure empirical phenomena might surrogates exploit? And it's a hard question. So again, going back to the surrogate decomposition, even if I find a surrogate, so first of all, choosing the right, it's not clear what is the right surrogate to consider. But we need to choose surrogates for which we could actually bound their generalization error. So perhaps surrogates that belong to classes where uniform convergence can hold. But even if we deal with this part, we also don't need to forget that we need to consider surrogates that can be connected back to the generalization error of the original classifier. So to the risk of the original classifier W hat. And so far in my work, I've only really dealt with the orange part. There is some work addressing the first bit, but again, as I said, there is no satisfying explanation yet, and it's a very interesting area of research. So let me just conclude now, and I can take questions afterwards. Good generalization is a product of favorable properties of the data, algorithm, and the interaction between the two. So the bounds have to depend on the training samples and the data distribution if we have access to, or perhaps we can simulate it to test our theories and see the explained generalization in deep learning. Empirical evaluation of the generalization bounds and measures is critical. Complexity terms that appear in the bounds are usually data dependent, and empirical evaluation is the only way to know how they grow, where the bounds may fail, and where we need to improve to make progress. So again, without empirical evaluation, I wouldn't have noticed a few years back that the norm terms grow too fast compared to the margin, or looking at Nagarajan culture work without empirical evaluation, they wouldn't have noticed that the complexity terms grow too fast with the data. So I really believe that empirical evaluation is absolutely critical to make progress. Capturing data distribution dependence by using training samples allows us to circumvent statistical and computational barriers when evaluating theories. And in both, in fact-based bounds and information theoretic bounds, adding data dependence added a huge improvement for the tightness of the bounds. And instead of bounding the generalization error uniformly over a hypothesis class containing the predictor, we should actually think about related predictors, so-called surrogates, that may belong to a class where uniform convergence holds. So again, this is for going around the barriers pointed out by Nagarajan culture and thinking where we can use uniform convergence, but perhaps indirectly on a related class. And so far, we have made progress in studying some surrogates. So by perturbing the classifier stepwise or at the end of training, but of course, there is still a lot of work to be done. The dependencies are, still not there. We can take more advantage, for example, of the past trajectories, perhaps in information theoretic approaches. And of course, there's a lot of work to be done on connecting surrogates to original classifiers. Okay, so I'll stop here. Thank you very much. And if there are any questions, I'm happy to take questions. If you have questions afterwards, feel free to email me, or if you want some references. Thank you.
Thank you, Carolina. So we have a few questions, and if you won't be able to answer all of the questions, I would encourage you to join our Slack, and we'll post. We'll enable the participants to post their questions on the Slack as well.
Yeah. So actually, about that, so I'm on Slack, and I believe there is DL Theory Carolina channel, and it's probably way better than email. I'm happy to answer questions there and have discussions afterwards if any later questions come in.
Thank you. Right, so let's start with the questions. First one is, does SGLD generalize better than SGD? Assuming adding a Gaussian noise at each step would help the algorithm escape sharp minima and prefer flat minima.
Yeah, so excellent question. And in practice, actually adding Gaussian noise makes the test error worse. So people define actually generalization sometimes differently. When I talk about generalization, I often refer to the difference between the test and train error. Or some people just talk about generalization as a test error, so the risk. But in any case, I'll just talk in terms of maybe test and train error, or risk and empirical risk, to make it a little more clear. So if you do add noise during training, such as in SGLD, you actually in practice end up with worse risk. So the performance of your classifier in practice does suffer. But if I recall correctly, the difference between risk and empirical risk diminishes. So the generalization gap or error diminishes. But I would say if you just want the best performing classifier, you will not be better off adding this noise. But it's really for kind of the simplicity of analysis that we want to study HLD.
Yep, thank
And
you.
that's, and just to add a little bit, actually, there's a lot of work now on kind of how, learning rare examples and small subpopulations is important for, or memorizing those is important for having small risk on those small subpopulations, such as work by Vitaly Feldman on short tail about long tail, or backwards, I don't know, something like that. So again, you can read more there as well.
Right. Yeah, let's move to the next question. Next question is by Dmitry. He's asking, how does the generalization connect to the work by Jonathan Franke et al. And on lottery tickets?
Yeah, so that work is my work, and it does connect. There are many answers that I could give here. So there is work in generalization theory on how compression improves generalization. So Backbase is actually kind of about that. There are bounds in terms of like minimum description length on connecting generalization. There are more recent approaches by so there is Sanjeev Arora, the work from his group. I apologize for forgetting other names that are on that paper on relating compression and generalization. There is a lot of follow-up work there. Victor Veach and his students, I believe, who worked also on compressing neural networks and showing that via Backbase it gives a generalization. So anyway, there's a lot of work generally on kind of, reducing parameter count or compressing gives a generalization. But from my perspective, there is a kind of maybe less direct link, which is for the surrogate analysis. So I mentioned that, we're interested in looking for structures, nice structures in perhaps optimization landscape, or, like various invariances that our learning classifiers have that can be connected to generalization through surrogate analysis. And I believe that my work on linear mode connectivity could potentially point the way, and we could potentially propose new surrogates based on the nice properties that we uncovered of linear mode connectivity. But it's a complicated question, and some of it is work in progress. So I'm happy to discuss it more in private, but kind of high level, I believe one could come up with creative ways to connect these things.
Okay, yeah, let's move to the next question. One more question from Dmitry. He's asking, could you explain a little bit more what, and I'm trying to pronounce it, vacuous means? And I'm sorry if I mispronounce it.
Sorry, say it again. Could you repeat, please?
Could you explain a little bit more what vacuous means?
Vacuous.
Vacuous.
What means?
Vacuous bounds.
Vacuous bounds.
Vacuous
yes.
bounds.
Yeah.
Vacuous
so
bounds.
by that I mean, so we're often bounding the error which is between 0 and 1, right? And we bound this quantity which is no more than 1 by something that's sometimes orders of magnitude larger, which of course does not, it doesn't give you actually a guarantee, right? If my error is between 0 and 1, which is how it's defined, and I bounded by 10, what will I say about my generalization? What will this bound tell you about generalization? So, so that's what vacuous guarantee means from my perspective. Of course, you could argue that maybe some constants are off, and actually for example, if I vary the number of parameters or whatever, some hyperparameters, perhaps my bound will still capture when my generalization error is increasing or decreasing. But in terms of the empirical guarantee, it's vacuous. So I have actually more on this work in our NeurIPS last year's NeurIPS paper on the robust measures of generalization, where we propose a way to evaluate theories empirically. So even if they produce numerically vacuous guarantees, we propose a way to evaluate theories empirically using notions from distributional robustness. So the idea there being that, not only you want to maybe capture, as you vary your hyperparameters, let's say, not only you want to capture how generalization error will change on average, but you actually want to robustly predict which way your generalization error will change. So as I increase my learning rate, I want to predict that my generalization error will go up or down, for example. Anyway, so there is a lot more in that paper, of course.
Right. Let's move to the next question. Lucas is asking if empirical evaluation is still necessary. Doesn't it make generalization bound evaluation similar to simple test error evaluation? Bounds still can be very different for different data subsets. We are ending up with the same problem.
Again, great question. And there's, a little more again in this paper that I just mentioned on the robust measures of generalization. So I see two extremes. One is the bounds that purely depend, that are very, very general. And for example, like the C bounds that purely depend on, the parameter count, let's see, and other notions of how complex your hypothesis space is. And another extreme is that you mentioned, which is evaluation on the held out set. But of course, there's a lot in between. So the held out set bound will only tell you for the specific classifier that I obtained, how will I perform, right? It doesn't tell you at all why it worked, when it works, what if I change some things or retrain, or even in the same setting, retrain in the same setting and try to predict again. It doesn't give you any insight. The bounds that we evaluate empirically, you evaluate empirically still maybe some kind of complexity measures that allow you to describe how your algorithm, hypothesis, class, and data interact, right? Or perhaps you can capture how hard your data set is, or any other aspects. So it still gives you a lot more insight, and it's hopefully will allow one to build better and more reliable algorithms in the future.
Okay, thanks. Let's move to another question, also from Lucas. He's asking, could you please list what topics in math planning in depth your last paper and other papers on generalization in general?
Okay, you cut out in the beginning. I'm really sorry. What papers?
Yeah. Could you please list what topics in math is necessary for understanding in depth your last paper and other papers on this topic in general?
Yeah. So I would say the starting point is just statistical learning theory. And there are quite a few good books and review papers. Actually, I can repost those on the channel. I posted it last time, but like the book by Scheib and David and a couple of other authors on understanding deep learning. The first few chapters very nicely introduced various kind of simple notions in statistical learning theory. And there are some review papers by Bousquet and many other authors. Then, of course, there is kind of the information theoretic analysis part, which doesn't really appear in these review articles. And for those, I mean, honestly, just looking over some recent papers probably would be sufficient to give kind of good background. But I can also look for better references on, maybe a few chapters in a book or a short overview paper that I can post in the channel.
All right. I guess it would be really interesting to read what you recommend. Let's move to the last question. It says, you mentioned that the empirical verification for generalization measures is important. Are you familiar with Ableton studies in a paper called Fantastic Generalization Measures and Where to Find Them, ICLR 2020? Is that the direction you imply?
Yeah, so I'm familiar with that work, and our work on the robust measures of generalization is somewhat a response to that paper. So in the fantastic measures of generalization, I believe kind of one of the arguments made there was that they're looking for causal measures of generalization. And I don't think that causality really has a role to play here. We may be able to explain generalization with quantities that are not actually causal. Acting on a generalization measure will not actually change generalization. And we have an example of SVMs, I believe, in our NeurIPS paper on the robust measures of generalization, where we kind of explain why causality is not the right notion, and something like distributional robustness seems more appropriate.
All right, so that was the last question. It was really great to have you here today. And thank you for the presentation and for your amazing answers. I hope that the discussion will continue on Slack. And we'll have a very short break, and we'll come back with Razvan and Viorica, who have an announcement for all of us. So we'll see you in a few minutes. Yeah, thanks, Carolina.
Excellent. So we are back from a short break. Very happy to see you all who stayed up until the end. But we want to let you know that it is not yet the end. We still have a few announcements to make. So now our co-organizers, Razvan and Viorica, will make an announcement about the EML projects that were initiated at the summer school a few weeks ago and continued up until recently. So they are going to talk about that, make a few announcements, and also make announcement about the future plans from EML. And once the announcements are done, we are going to transition to a panel discussion with Dovydas, Viorica, and Razvan, and I will be a moderator. It's going to be a brief panel discussion on also kind of the future plans and how Lithuania could get more involved in the international AI community. So passing on to Razvan, I believe.
Cool. Thank you. So this year at EML, we've tried something new. So we tried sort of having this project that would be continued until the workshop. And the motivation for this is because we believe that the most that participants can gain from events like this is building their network. So this is probably way more important than just listening to lectures and sort of connecting to the speakers. Sort of this kind of networking that you could do, this is sort of what will help propel you in the field and sort of give you the ability to do the kind of research you'd like to do. So to have this happening, we wanted to get students to work together. So if we can go to the next slide. So the idea was quite simple. Is to allow participants to self-organize into teams that had at least 4 participants, with the intent for these participants to be from different institutions, because the whole goal was to try to get sort of people to communicate. And yeah, if they would be from institutions from different countries, that was even better, because that's usually, it seems to be a barrier, particularly in Eastern Europe, seems to be a barrier of people communicating between sort of neighboring countries. And then each team would brainstorm on a project that can be done in the time frame that we had, which was roughly 14 days, and then would present this plan during the school. And we had 6 such projects presented, and then they would try to work on their proposed project until the workshop, and submit a small report on sort of what they've managed to do and sort of explaining the project further. And based on that, we would like look at them and would figure out what the winning projects are. And we've done that yesterday and today. And I guess I'll leave it to Viorica to say sort of what the outcome of this was.
Okay. Thank you, Razvan. So yeah, I'm very pleased to announce the projects first, just to list the projects that we've received. So we've had initially 7 teams at the school, and 5 of these teams committed to work on the projects until now, until the workshop, and submit reports summarizing their work. So we have to say that we were really, really impressed with the amount of work and effort that you managed to put into this short amount of time. So we are very, very pleased with the outcome of this experiment. As Razvan said, we tried this this year. And we hope that people will feel motivated to seek this kind of collaborations in the future. So we will surely repeat this kind of program at the next year's edition. So just to list the projects that we've received. So we had 1 project on continual learning, 1 project on cross-lingual Eastern European natural language processing index, 1 project on creating a tutorial for next year's edition at EML on explainable deep learning, 1 project on applying generative models for generating medical data, and last but not least, a project on self-supervised sample efficient reinforcement learning. So yes, as Razvan mentioned, we've went through the reports, and we tried to evaluate them based on their potential impact, based on how much effort we could assess that went into the project, and also based on what we think could be the outcome from a research perspective, and also, as I said, a social impact perspective. And yeah, we are very pleased to announce, let's say, the winners. And So these are the winners in terms of prizes. I'll just explain very quickly what these are. So like the winner, the first winner, we consider to be this cross-lingual Eastern European NLP Index. And for the authors of this project, they will receive admission to next year's edition without selection, plus mentorship if they if they continue to work on this project. And this is at least what they said in their report, that they will continue. So this is actually an impressive project. They've managed to put together in these 2 weeks a ton of resources, and these are all now available on GitHub, where they listed existing data sets in Eastern European languages. They've listed large BERT models that exist for different languages. And they even created some baselines for a few of NLP tasks. And all of these resources are now available online. We will surely tweet from our EML account because this is a very valuable resource for the community. Next, the second, let's say the second prize goes to the explainable deep learning tutorial. Which needs a bit of cleanup, but we are very pleased with the shape in which it is now. So there's a lot of good content there. There's a strong start. So the authors of this project receive a conditional admission to next year's edition without selection. So conditional means that the authors need to clean up the material and to bring this to a final tutorial. And we commit to provide advice to bring this to the final form. This tutorial, it will depend if we will actually run this as a tutorial at next year's edition. It will depend on the program that we'll have for next year that we don't know yet. But we will surely at least recommend to the participants to go through this tutorial before the school, because it has a lot of good content in it already. And for the remaining 3 projects, the organizers pledged to offer mentorship for these 3 projects to work towards a paper, because we saw very interesting ideas, research ideas there, hypotheses and plans to work towards a paper. So if the authors of these 3 projects are interested in pursuing these directions, we will seek mentorship for you to help you to work towards a paper and submit to a top machine learning conference. So again, thank you so much to all who got involved. We are extremely pleased. As I said, we are extremely happy with how this turned out. And yeah, thank you so much for getting involved. And yeah, we hope that you enjoyed it. You enjoyed working on this, and that you created interesting connections while working on the project. So I think this is all for the awards.
Excellent. Do you have any more announcements to make in regarding to the summer school, or are we proceeding then to the panel?
I think we can go to the panel.
Okay, excellent. Okay, so hopefully everyone is ready and excited for the awesome panel we have. And it's going to be the 4 of us, Dovydas, Viorica, and Razvan, and I'm going to be the moderator. So I guess the first question would be to both Viorica and Razvan to tell a bit more of a backstory, how you started with EML, and how you worked with different countries, with different communities, kind of to try and create larger representation of Eastern European countries at conferences like NeurIPS, ICLR, ICML, etc. Because if you go to these conferences, they're quite large and mostly Western countries dominated. So it's quite interesting to see like what your experience has been so far and what is your strategy going forward. Either of you?
Okay, maybe I'll just start very briefly. So the discussions around EML, like starting EML, started back in even 2016, I guess, the end of 2016, when we were at a big conference, I think it was NeurIPS in Barcelona, and we were discussing with researchers from Romania about the fact that there are not enough experts in Romania to develop machine learning projects and to do research in Romania. So, and we kind of pinpointed this to the lack of good educational programs in Romania, like master's programs that do AI and machine learning. And we said, okay, maybe there is a way for us to set up such programs and to facilitate access to education for students in the region. And that's kind of how we thought that, okay, setting up a master program is a very big thing, a very difficult thing to do. So we said, okay, probably a first step, doable step, is to create a summer school and then to gauge interest, to get an understanding of the interest from the universities and the local companies and just the community overall, and then to see how we can move forward. So that was kind of the starting point. And we were really surprised and pleasantly impressed that we received so much support from the local communities and interest from the students and the universities and companies. And that's how, yeah, we've decided to set up this program. So Razvan, maybe you can also share your thoughts.
So maybe I guess besides the discussions we had at NeurIPS in 2016, I remember another component that really convinced me to go for this was I got invited to go back to Romania to give a talk. It was one of this kind of machine learning meetup. And like one thing that surprised me was sort of the expertise that people had there, right? So there were lots of students. They were up to date with the latest techniques and everything, and they were playing with all kinds of cool models. But like you know, they probably didn't have like you could tell that they didn't have the same visibility, and they didn't have sort of the connection with the Western world, like you know, and even like the way they were asking questions, right? They were kind of scared and just kind of going forward and asking questions. So we thought that that was something that convinced me that like an event like this would help quite a bit. First of all, just for them to see sort of that they're already at a really high level, which maybe is something that they didn't know themselves, and then just sort of to help them connect them with sort of the rest of the community. And I guess this is also partially why we didn't go for like an event that's specific to Romania, because we feel like sort of this kind of connectivity and, you know, trying to make this kind of network and communicating, it's extremely important. And if you'd have an event that would be just for Romanians in Romania, that would actually not help at all. Like you'd actually want quite an international event, and try to connect, you know, as many people as you can from different communities, and try to get these communities to speak between them, because there's a lot of there's a lot to be gained from having this. So and then the sort of how we kind of settled on this idea of having like a summer school meant for the Eastern European community, we started in Romania because, as I think we've mentioned this before, it was easy for us. We knew the local context, but with the explicit aim to kind of just move around from country to country and to get to know as many communities as we can and try to connect them. And we've managed to do that to a certain extent, right? We've managed to get to Poland, we've managed to get to Hungary, and we've managed to get now to Lithuania and to Ukraine and other places through the workshops we did.
Excellent. Thank you so much. Very interesting. So my next kind of question would be now to Dovydas, who is the co-organizer of the event, but is also a president of Lithuanian AI Association, which has multiple people joining it, multiple representatives from both industry and academia. So maybe Dovydas, you could share the same kind of idea and story that was behind creating the Lithuanian AI Association, and what has been the path so far, and what is the path forward, and what are the challenges?
Muted. So thanks, Jeff. Yeah, so the Artificial Intelligence Association of Lithuania is like our attempt to get all of the industry experts and also a lot of people from the academia to have like this joint forum and joint like maybe group of experts, so we can share knowledge, like what works, what we can do, and how to represent what we are actually doing in machine learning and artificial intelligence, so that the like groups that are interested in these topics, so that they can have maybe not I don't want to say an unbiased picture, but like as unbiased as it's actually possible, so that we can understand that this AI is not it's not the artificial general intelligence. First of all, that's a pretty recurring topic. It's not something that has to be thought about in the future. It's like a thing which, like all of us do today. It's a thing that requires help from various other stakeholders, the government, the industry, the academia also, which needs to be understood. And these experts and these industry and academia experts, they are bringing quite a bit of value to Lithuania, and like if the country would help them back, or I guess will enable them, it will like these efforts will be like they'll worth their while. So in short, we just want to have this like representative community, and also like knowledge sharing with the knowledge sharing mechanism amongst the members also.
So in both cases, it seems that the emphasis has been on building the community first, then building the networks for these communities, ability to interact in between for the people within the communities, and also solve the challenges that the members within the communities might have. And also, I guess in some cases, also educate those who might not be members of the community yet, or might be thinking of becoming members of these machine learning communities. And I guess the good question here was that I believe you mentioned, Viorica, that in Romania before you were considering even starting a master's program. So was that successful or was it not? Like how did you approach that?
So we've discussed with a few local universities about this, and we've discovered that actually there were masters that do artificial intelligence, but some of them doing a bit more traditional artificial intelligence, not focused on machine learning. So basically, we just try to support the local programs and get involved as much as we could in different ways. And for example, in Timișoara, we contributed and helped launching a master's program. So we organized a similar machine learning workshop there in Timișoara in Romania around the time when they were launching the master's. So we've announced this launch at the workshop. We've also collaborated this year exactly with a professor in Bucharest, and we've invited lectures at their master's program. So they have a master's on artificial intelligence and computer vision, and myself, Răzvan, and another colleague from DeepMind, we went as invited speakers at the master's. So we've tried to get involved as much as we could in existing programs or in setting up new programs. And providing feedback on their curriculum that they're setting up for the masters. So I think we are seeing good signs. Like the community is really building up, and we are really impressed that all these efforts, they also have a backup from the industry side, which I think is really important to have the companies also involved in this.
Okay. Excellent, thank you. So as far as I'm aware, in Lithuania, we already have quite a few kind of master's programs and different other academic programs. But maybe, Dovydas, you could mention what are the challenges Lithuanian AI community is currently facing, either from industry or academia point of view?
Yeah, it's not an easy question. There are, layers and layers of challenges. And I guess I need to make on the spot, make a very good ranking of which of these problems are important. So by the way, if I'm not mentioning them, they are still very important. I just have to pick the most important ones. Personally, I feel that what brings publicity and success and maybe interest in the machine learning and AI are currently startups. And we have even as association members, we have a few startups which are doing pretty amazing things, and people are getting excited. Like, hey, I can now help people using deep learning. I can understand the X-ray scans, and I can detect the cancer, and I can detect other diseases with much higher precision than it was previously possible. And I don't really need to get a medical degree to help people. I can still be an engineer. I can still work with computer vision, and I can still feel have this impact on not only my local community, not only the people in my current hospital, but I can have this algorithm deployed worldwide if it's the best algorithm. And I think that these startups and helping the startup community to really apply this already super powerful algorithms which are already developed, but we are not not enough products have yet been built. Leveraging these amazing achievements in the especially I'm maybe focusing too much on deep learning because it's just provided such a wide spectrum of new algorithms. But I mean the rest of the machine learning ecosystem is also improving quite a bit. So things that were impossible even a couple of years ago are possible now, and some products which were impossible a couple of years ago are possible now. So I would say this is probably the number one, helping the startups to take off the ground, helping them with financing, with mentorship, with product development, with even with things like data science or machine learning project management, because that's a totally new thing, and we are constantly learning something new invented, like how to manage machine learning projects and how they are different from typical software engineering projects. That's the startups need a lot of help in that, and I believe this is maybe one of the very, very practical number one thing to tackle. Of course, there are other things like, for example, data openness. That's again, so many people in both academia and the industry would benefit if the data would be more open. I mean, data from the government and other companies. It seems like right now we don't have enough of an infrastructure or even the legal base to share the existing data sets because everybody's super restricted. I mean, in terms of interpretations of laws, even GDPR, it's very easy to interpret that hey, I cannot share literally anything. While in fact it's not true. You can share quite a bit, and sharing this data, sharing data sets, it's the lifeblood of what we do in machine learning. New data sets leads to people hey, I have this data set, now I need to just flex my machine learning muscles and I can make something great. So sharing data sets, I think, is the second most important thing. And to have a top three, the third one would be collaboration between the industry and academia. And I'm very actually curious. I really would love to hear Viorikas and Razvan response to this question. What do you think would be the best way to have this collaboration happening between the industry and academia? Because I think that Lithuania is starting this. I see a lot of great efforts coming from the academia, but I would love to know what are your take on this. What do you think would work?
Okay, maybe I can start this time. It is sort of a hard question to answer, particularly because for me personally, I haven't been involved that much in sort of setting this kind of things up. So I don't know. But one thing that is important is for industry to realize that it is useful to invest in sort of open-ended research questions. And at least I feel that for more traditional companies, or for companies that don't have a lot of budget to go around, they tend to be investing in very precise projects where the goal is like, okay, I need a PhD student to do X, Y, and Z that can directly fold into my production line, and it's not really research. And this kind of investments, they actually hurt academia. You get sort of the sense that the students end up not doing research. Basically, they end up kind of just working to a certain extent and just applying traditional methods. So I mean, so that's sort of one on the industry side. I think it's sort of the openness of just investing in research and in open research that might not give them any kind of short-term benefits, but would give long-term benefits in sense of developing the community. So there's going to be a lot more experts out there that they could hire later on, or just sort of improving the tools that somehow will end up in their production line. That's, I guess, sort of on the side of the industry. The other, on the side of the academia, I think there's usually like setting up a connection with an industry partner can be relatively complicated and bureaucratic. I don't know sort of how the situation is in Lithuania, but like that ends up being an issue where somehow most of the money end up to the university rather than to the lab or to the people who are supposed to work on that project, and ends up going through a lot of paperwork and a lot of walls that are not useful. So one way that I've seen this being resolved, and this happens in the West as well, is by setting up this kind of institutes, so like Mila and so forth, that basically now have their own legal framework through which they operate, and they kind of avoid to a certain extent the bureaucracy that's involved in like dealing directly with the university. Depending on the university, some universities are also very I mean, I think this is an issue on both sides, but they're like very strict with IP and things like that, which can cause problems or can make this kind of collaboration difficult. So again, as long as both the industry partner and the university agrees on sort of the research to be open and sort of published, and the data to be public, and kind of are not too strict about these things, then things can work. And yeah, in my view, it's just sort of understanding that long-term that would benefit a lot more than whatever short-term lack of gains they might have, because they gave up some IP, or they've opened up some data that was just theirs, or stuff like that.
So maybe just to add, like from my involvement with the community in Romania. So we've worked on setting up a project, like exactly what Răzvan mentioned, like an institute, a local institute that would bring together, like that would represent a bridge between academia, industry, and then the public, like the government and the public authorities, because I think such a bridge is really, really important to have, because at least in Romania, for example, there are not that many frameworks, or it's not easy if a company wants to pay to have internships, like to host interns from academia. There's not even a platform where they can advertise such positions, or and there is not the communication doesn't happen easily, because also the academia doesn't have in place all the legal frameworks for paying or for accepting funds from industry to cover like internship costs and so on. So I think setting up like this kind of institutes is really crucial. And the way we were seeing this is to have an institute that has a strong research component, where you'd have both fundamental and applied research, then to have a strong educational component, where this institute would oversee the different educational programs in the country, like from undergrad, even high school, because we are working on kind of a program for high school to teach basic concepts of AI. So to start from high school, and then undergrad, masters, and PhD, like to have an integrated view of the education in AI. And this would be possible under the umbrella of such an institute. And then, of course, a very a crucial component would be this part that connects the academia with the industry. to ensure that whatever research results you have in fundamental research, for example, you can transfer them to industry in a timely manner. So I think such an institute for every country is really very useful to have, because in every country, I imagine there are some institutes already existing, but they did not, at least when they were created some years ago, they did not focus on this strong connection with the industry. And I think this is something that is missing, and it's really needed. So yeah, having such institutes, I think, helps a lot in every country. And then we've also trying to propose ideas of professorships sponsored by the industry, because this then can bring can make a stronger collaboration between companies and academia. Because what we also see often is that the salaries in universities, they are not sometimes they are not competitive with what those experts could get in a company. So then there should, like we are saying, that there shouldn't be a competition directly between academia and industry. There should be more collaboration. So this model exists in the West. There are companies that like DeepMind and other companies, they sponsor professorship positions in universities. So I think it would be great if we could start seeing something like this in Eastern Europe as well, because there are many local companies that need talent in AI. And then if they understand that by sponsoring such positions in universities, these professors could grow teams, could grow research teams, and they would provide in the end the talent for that is needed in companies. So yeah, I think these are some ideas, and of course and maybe without, I don't want to make publicity for DeepMind, but for example, we have created now this scholarship program where DeepMind funds some scholarships at master level in different Eastern European countries. And I think it would be great if other companies followed this example, and also to fund such scholarships. Because what we see often in Eastern Europe is that students, besides doing their masters or their PhD, they also have like a full-time job on the side. But then that kind of impacts their performance on the research part. But if we have companies that are willing to cover like good scholarships, then they can focus fully on their research. So yeah, these are some ideas how the industry and the universities could collaborate to build a stronger community, basically.
Thank you. That sounds definitely like something that potentially Lithuanian AI community could take on and start to promote these ideas. One thing I wanted to touch on, since it was talked quite a bit, mentioned by quite a few of you, that the question of freedom, of academic freedom, and the research that people do, so kind of, and that's also stands at the boundary of collaboration between academia and research, that sometimes academia and research, industry and academia, that industry might have a specific agenda that you need to do that specific work, but then on the other hand, if academics have all the freedom and the incentives for them to be independent, let's say at times when needed from industry, they need to have sufficient incentives. And one of the items in Lithuania, which I understand is quite painful for computer science, is the question of indexing journals. And I was wondering if you faced with such challenges in other countries that you worked with.
So maybe I can start, and potentially Viorica can fill in the gaps. But yeah, definitely that tends to be a problem across many countries. In Romania, we have the same issues, and it can get to as bad as having papers accepted at NeurIPS ICML likely not being recognized for your PhD. So you need to somehow have that paper published in some journal that definitely doesn't have the same quality or the same kind of and then this is a big problem. and unfortunately, it harms. I don't, this is not even on the industry side. I think this just harms academia in general because it kind of ends up in sort of this closed setting where many times you have these very hyper-local journals where most of the publications come from the same university or from a couple of universities, and it just kind of loses meaning to a certain point. There's been some changes. So, for example, and I don't fully know all the details, but I know, for example, this was a situation in Poland as well, but it changed a couple of years back, where they've tried to update sort of how they evaluate these kind of things, and they've managed to include sort of the conferences that matter for machine learning, for the machine learning scenario. So this change can happen. It probably needs a bit of top-down influence as well for it to properly happen, because there's a lot of momentum in the way things are. So it just bottom up can't be fixed. I've also, like, just talking to people, for some of them, like, sometimes you just find workarounds. You do end up wasting a lot more energy because, besides submitting things to iClear or whatever, you need to kind of make a journal out of it afterwards. So you'll spend like an extra couple of months just to kind of make that into a journal. But there are some people who kind of try to make it work, and I think that's kind of a start. But yeah, I guess it is still a big problem. And maybe just to add to that, this used to be a problem in other places as well. So I remember talking to Doina at some point and mentioning that a few years, and that's a bit more few years back at McGill for her department, they had sort of kind of similar issues where some things that she thought were very relevant weren't necessarily in her department thought as being the right places to submit. And so it's not like it's a problem that existed everywhere, and it's kind of slowly changing. And I guess it's just a matter of us as a community putting pressure, and then things would probably end up changing.
Yep.
Maybe to add, like, on a different dimension to this, like, of course, there's this problem of conferences not being indexed properly or journals. But I think there's also a problem with the costs of such venues sometimes. So at least for the in-person events back 2 years ago, attending a conference, like a top machine learning conference, computer vision, whatever, that requires a lot of money. And in Eastern European countries, I'm not sure what's the situation in Lithuania, the funds available to a PhD student to travel, or even to a faculty to travel to such a conference, they're very, very limited. So even, let's say, even if your university recognizes such venues, you might just not have the funds to attend it. So I think that's a big issue. And I think in this direction, it's also the community, like, from these conferences, there should be some changes. So there are some efforts now to provide scholarships for students to still be able to attend if they don't have the right financial support. But I think there should be more efforts in this direction. And yeah, so I think this is something that we can do, like, from the West, let's say, if we are involved in organizing such conferences, or if we have more influence in this. I think we should pay attention to this and really strive to have more inclusive venues, such that just I don't know, some financial aspects don't prevent people from attending them. So yeah, I think that's also important.
Excellent, thank you. Now I want to remind everyone who is watching us that you can still ask questions on Slido, and I will make sure to read them to our panel participants. So please do make sure to ask questions. Now I'd like to get now to Dovydas, and since we kind of talked about the incentives, and you also mentioned about the role that startups and industry can play, and I was wondering if you could comment on the situation in Lithuania. What are currently industry members in Lithuania are doing to kind of proactively work with academia, or kind of create the incentives for the kind of the community to grow, or maybe even apply some pressure to make the necessary changes?
Yeah, so it's again a very good question, and I know that some I guess at this point we are more of an individual level pressure appliers rather than company level pressure appliers. And I know that some people in the association are actively working and trying to fix this academic indexing problem. They are trying to get the conferences recognized. I think that the collaboration, as you mentioned, the collaboration has always two sides. I think that the collaboration is kind of happening via people who are actually in both. Like some people are both in academia and in the industry, and they seem to be the bridges which try to to prove to like, hey, I'm like benefiting from being in the academia, and I'm benefiting from I'm more valuable to the company because I am in academia, and I'm more valuable to the university because I am working in the industry. And I think that at this level, these I would say really amazing people like kind of are proving with their own example that this collaboration is valuable. I would obviously love to see this moving faster and more in a more I guess less individual way, but more systematic way. But even what we have right now, I think is a good indication of a start. I would love for I guess one I guess the industry or the universities to step up and cover the gap and extend the hand and say, hey, let's if we collaborate, we can do a lot of great things. And actually, we are also doing that right now as a company. We have a collaboration with a PhD student. Actually not from Lithuanian University, but already we are seeing value in this collaboration. The student is helping us with our A/B testing setup and like estimating if we have biases in how we do A/B tests. So this is a great example, like how like a person from academia can help out like a company to actually not help out in a like some kind of unclear or unmeasurable way, but in a very, very clear business value adding type of way.
Excellent. Thank you so much. And I guess let's check if we have any questions on Slido. No, we don't have any questions on Slido so far, but hopefully we will get some. If not, we will run an auction just like we did yesterday on our last quiz. But one of the questions I'd like to ask, what we see in kind of countries like Lithuania or countries that participate kind of in the Eastern European machine learning community more broadly, that quite a few researchers like yourself, Razvan and Viorica, you work abroad. And what do you think you can do to kind of help younger researchers that are in Lithuania, that are in Romania, in other Eastern European countries, when they're at the start of their PhD and they don't necessarily have the opportunity to go to the, I don't know, NeurIPS, et cetera, et cetera.
Okay, so most of us, so many of us who are working in the West but are originally from this region, many of us, we do want to contribute back some way, and we're kind of open to all kinds of things, like giving lectures, discussing with students, mentoring them one way or another. I think many times there's not like a particular forum that makes this easy. There's not a particular way of doing this, and you kind of need to find your own way to reach those students that maybe are in need of help and kind of help them. There's also, I feel like the other way around. I feel like students are maybe less likely to kind of reach out, and they should reach out more and sort of try to build those collaborations, because there is sort of this, like all of us feel this sort of need to help out when we can, in the way we can. So I think pragmatically that would be sort of like hands up, like if I'm to do something tomorrow, like there's definitely the kind of things that can easily happen, having this kind of events, offering mentoring or guidance to students from time to time, maybe being invited to give a lecture or being invited to have like a discussion with students on a particular topic that you have expertise on. The other thing that I think it would be nice to have a lot more of it. I think there's a lot of advantages in sort of allowing people from outside to have like double affiliation to things that are happening in a country. And it might seem like it doesn't bring much, but I think it does. Sort of, even if you have someone who's, I don't know, associated with the research institute in Romania, but that person is never in Romania or never in Lithuania, you know, they completely live somewhere else. I think that can still bring value. So I think, you know, this should be something that the community should try to exploit a bit more and sort of try to create these kind of opportunities and occasions where, you know, they can attract, at least in name, to kind of, and then they're sort of just kind of opening the doors, right? That just creates that channel of communication through which, you know, you can find like support and mentoring through that person and so forth. So this is another idea that I think could have quite a bit of value. Sorry, I had a few thoughts in mind, but I feel like I'm blanking out. The other thing that I wanted to mention is that I think the local community could also rely on the diaspora to kind of help them with things like, you know, like reviewing. So, for example, I know, you know, I've been invited multiple times to review projects for like EU or for like Canada, for CFAR and so forth. I haven't been invited that much to review projects that are going to be funded by the Romanian government. So definitely there is you can rely to kind of ask for guidance and to kind of figure out things like this whenever there is a chance, and you know, so that would definitely be one thing to consider from the local community, to try to rely on these people sort of for their expertise, for guidance on where to go. And the last thing I wanted to add is that so this is an observation that Max Welling did at the summer school, which is it is sufficient to attract one person from outside to come back home to make a huge impact on the local community. And the example that Max gave was the example of himself, where he came back to Amsterdam, and he came back for personal reasons, from what I understood from the discussion we had. But like, you know, just getting someone who already kind of made a name for themselves to come back, that could have a huge impact on the local community. And like trying to do that as much as you can from time to time is definitely something the local communities should try to do. And there's always reasons to come back home for, you know, personal reasons and stuff like that. So it's worth always trying, even though it seems like a very, you know, asymmetric choice, where like, why would someone, you know, come back from, I don't know, Stanford to Lithuania? But there are always reasons to do that. So it's worth trying to do that.
Excellent, thank you. I want to remind the people who listen to us that to keep submitting Slido questions. The auction is on, so please submit the questions. And I see, Viorike, you wanted to make a comment as well.
Yeah, so maybe just to add that I think researchers from abroad, they can really get involved into strengthening the local communities. So as you're saying, like in Lithuania, you already have this Lithuanian AI. But like in Romania, we contributed to starting this like an informal community where we just have like we have a Slack channel, and then we have like a web page where we try to index different research groups that work in machine learning and different projects. And I think we did a decent job there, because like we've worked together with collaborators in this community in Romania, and we created a benchmark for Romanian language tasks, and this benchmark was not now accepted at NeurIPS for the benchmarks track. So I think this is an example of how researchers can really get involved with researchers from their home countries, and really to promote the research and support the community there, which I think it's always a helpful thing to do. And maybe one more thing, as Răzvan mentioned, the idea of reviewing projects to be funded by governments. We are also trying to get involved with giving advice on drafting a strategy for AI in Romania, because like different countries, like the more developed countries, they started like France, UK, US, starting Canada. They drafted AI strategies for the country to have like a joint effort in making progress in AI. And smaller countries in Eastern Europe, they don't really have much strategy, like from the central point, like from a government perspective, to have a strategy to develop the field. But I think like the local communities need to put pressure on the governments to start thinking about that if they don't do that already. And then people from abroad, they can really help with that, like to give input on how to draft such national strategies.
Thank you. I'm actually so glad that you made an introduction into this topic, and I don't have to introduce that, the conversation of the collaboration with the government about the AI strategy. So actually my next kind of topic and question was to you, Dovydas, is what is currently going on in Lithuania in terms of the AI strategy, in terms of the reviewing the kind of documents? What is the position that the Lithuanian government currently takes, and what is the stance that Lithuanian AI Association currently takes in regards to that?
Mm-hmm. Yep. So thanks, Jeff. I guess it's not like it's pretty hard to like very concretely answer this question, because like as maybe people who work with the government know that people with the government know that the policies tend to change quite a bit. And if we continue to, like, I mean, sometimes it seems that what we start to do, like collaborating with the government, it seems to me that sometimes these good initiatives tend to die off without, you know, any other reason that hey, just the minister changed and now they are prioritizing some different things. But like we have some governmental organizations who are pretty active and pretty, I guess I would say I'm happy with their current level of competence. And I really hope that like this, the collaborations which we currently have will be extended in the future as well. So we are also, like as we mentioned in the introductory like welcoming talk today, we are organizing together with actually one of these companies, AI Boost. We are organizing an AI conference in November, and I think that these like educational, promotional, and actually like I guess different types of educational programs are what's the most valuable right now.
Thank you. Could you elaborate a bit maybe on AI Boost, and is it kind of some sort of a ministry organization that you're working with? What kind of their stance is? What is their goal in Lithuania? Kind of provide some context.
Mm-hmm. Yep. So we have been collaborating with the AI Boost for, I guess, the last couple of years, and this it's like a governmental organization who is dedicated to, like as the name I guess implies, boosting the AI in Lithuania. They are owning various different initiatives. One of them is a podcast. They're also doing a lot of promotional work. They tend to help out in like community organized events. We also tend to like together with actually with the association, we tend to represent like our industry experts, but like regarding to, let's say, European Commission proposals regarding the AI. Even I guess like a few months ago, we had a few comments which the AI Boost helped us actually to get across to the European Commission, like regarding the new regulations. So we are like this serves like an excellent bridge to help us out in delivering our like the I guess position of our members to help our members reach the decision makers regarding the new decisions regarding the artificial intelligence. And I guess this is very appreciated, and I'm very happy that this organization exists. I would be, I guess, even more happy if like the community would be a bit bigger and we would have a more representative voice. Because right now we have like we have a lot of experts, but as you know, like the more we have, the more of a like representative voice we can actually have. So like if we don't have I don't know, some like a significant cluster of researchers or industry experts, then their voice is not being heard. So I think it's very, very important for us to you know, have members in various institutions and companies.
Excellent, thank you. So I do have now a few questions, and we are gonna start answering these. So the first question is, maybe you have some, it's asked by Mantas Lukashevicius, maybe you have some comments about the education before university in different countries. I know that, for example, Romanian schools give a very strong math background to students, while in Lithuania, the standards are probably even sliding back, ...
So maybe I can start and then the others can fill in the gaps. I mean, there's definitely a variation from country to country, and but I would say, like, if we take the example of Romania, like, we traditionally tend to be quite strong in math, but at the same time, the way the curriculum and the way the teaching is being done is in a way that doesn't really help students to think in sort of in a creative way. So like take a very specific example. You learn about derivatives. The way you learn about that, you know, you get a bunch of formulas that you need to learn by heart, but you never know exactly what they're useful for, or like how do you, what is the semantics behind them, right? So you learn a lot of math, but maybe you don't necessarily learn why you learned that math. While I would say in other places might be the other way around, where you kind of focus a little bit more on the understanding, but maybe you don't get to some of these concepts. I mean, there is variation, but I think there are a lot of concepts about machine learning, and because we were talking about this before, that are intuitive and generic enough that will probably apply in any kind of situation. So as Viorica mentioned, we started doing thinking about like making a curriculum for high school, like an optional, you know, kind of curriculum for high school for AI. And the way we done that is we first started doing it in English, just because that, you know, allows multiple eyes to look at it and kind of reason for it. But then when you try to think, okay, like I would want to have this being done in Romania, then, you know, besides just translating it, you need to adapt it to the local, you know, exactly what they would know and what the students would not know. So I mean, I guess like when we're thinking about like pre-university, and if we want to teach concepts of ML, that, you know, those might need to be tuned to the specific context of each country. And that's why we need the local communities to be interested in, and because those communities are the only ones who know what is the exact context within, you know, their country, and like how topics are approached in high school, and what kind of concepts they're taught and what kind of concepts they're not taught, and which aspect of this are important and which are not. But yeah, like in ML, high-level concepts like the difference between causality and correlation and things like this are important, not necessarily because you want to become a machine learning researcher and do research on this, but you're using these tools every day and you sometimes don't understand what they do. So understanding sort of some of these core concepts can help you understand what this tool can do for you and what it cannot do, and then sort of reason about that, because if we don't reason about that, you can end up in all kinds of weird situations.
So maybe just to add, like related to this machine learning course or AI course, so we're not just thinking about it, we are really close to finalizing the materials for it, like translating them in Romanian and so on. And we really think that such a course could actually show students why it's good to learn programming, why it's good to learn maths, why, you know, because it links so many things together, like, and then you see why you should learn about these concepts, because yeah, exactly as Razvan mentioned, we're learning about these concepts, but in a very abstract way. They are not related to real problems, and yeah, some people are just not motivated to learn about them if they don't see the final utility. And I think if we can come up with very simple projects that would link, I don't know, related to biology, related to chemistry, and that bring in like programming for designing such systems, and then you explain a bit the maths behind it. So you have a really nice integration of different disciplines that could really motivate people to get into this and learn, because they would see the final application of this, it's not just an abstract thing. So yeah, I'm really hoping that we will make progress in introducing this course in high school, and then we'll see how that goes. We've run already some pilot courses with a few students in Romania and teachers, and we've got good feedback on this. So yeah, once we run a pilot on this in a few high schools, we'll see how that works.
Okay. And Dovydas, maybe you have something to add as well, because as far as I'm aware, you were quite involved in data science education in Lithuania. So I'm sure you have something to comment.
Yeah, I'm very passionate actually about educational part, and I don't want to go in like a 45-minute rant here. I don't think it's the right place, but I would like to maybe say one thing which I'm actually very happy with, and which I hope that will like improve everything in the long run. So first of all, like Mantas is saying that Lithuanian standards are probably sliding back. I don't have an analysis like about the historical results, but the last thing like regarding the math scores I remember is that we are like I think almost exactly at the OECD average. So it's not like, first of all, it's not, we are not starting in a very terrible place. We are not dead last in like the maths. But what I think is very important, and I really hope that like Lithuanian students will get this message. Maths is a path to a good job. An interesting job, a job which you can apply your creativity, where you can apply your reasoning skills, where you can apply like pretty much if you like these things. Maybe not like math sometimes can get like a bad name, being very, you know, like just very theoretical science, and with not a lot of applications. However, I think this thing is like drastically changing in the like last maybe just last decade, because like we have more and more data science type of professions, like including machine learning researcher, machine learning engineers, data scientists, which requires strong understanding of mathematics, but not in a pure mathematics way, but in a very applied mathematics way. And these professions are very well paid. They are very important. They have a lot of value to the companies. You can, like, knowing mathematics will enable you to have a huge impact in the company in which you work, and in addition to that, you'll make like quite a good salary by doing that. So I hope that this trend, this like very concrete reward function, like learning math has a very good reward. I think this will like enable students to pay more attention to this subject, and will enable us to have more mathematically inclined students in the future.
Excellent. Thank you so much. I got very inspired to learn math, go back to school. Okay, so we are running towards the end, and we're going to ask one more question from the audience. And the question is to you, Viorica, by Lucas Martak. Lucas is asking, regarding the monetary barrier of BigML conferences for academics in some countries that you mentioned, is there a particular approach you'd prefer seeing being taken in the near future? For example, more Eastern venue locations? Thank you.
So yeah, I think we've made this argument back when, after we've organized the first summer school back in 2018, we've written a report where we were advocating exactly for this, more Eastern European locations for such events, because there are so many benefits to it. Like, it's cheaper to organize for the same quality and much better quality. Like, I think the way we organize the school, I don't think many other summer schools in the West organize those kind of events like we did in Romania. And yeah, we didn't get to do it in person in Poland, but like, we're able to offer an experience, where people can get to know the local culture, and having dinners in very nice venues, and having panels in traditional, like, historic places, to really get to know the local country and the local culture. And I think you can do those with costs much reduced compared to what you have in the West. And there are really not many barriers to organize events there, because we had support, like administrative support to organize the events. And yeah, the costs are affordable. So yeah, I think definitely we are really advocating for more events in Eastern Europe. And yeah, maybe we don't have like the logistics for events of 10,000 people or 20,000 people like the big machine learning conferences now. But I think there would be value in attracting at least the smaller ones to have them there. So yeah, definitely I am a strong supporter of having more events in Eastern Europe.
Excellent. Thank you so much. So in the interest of time, I think we'll be going towards the end. I see there is a question by Auxas about who should take the first step between industry and academia, as I understand. And I believe we've talked a bit already, quite extensively. So I think at this point, we are going to wrap up with the workshop and with the panel discussion. Hopefully you've all enjoyed the panel discussion, and naturally we invite you to continue the conversation on Slack. If there is something that you disagree with that we've said, or something that you strongly agree with what you said, please do voice that. We want to hear your opinion on Slack, on social media, anywhere possible. So please do use all of the resources available. And I guess at this point, we very much thank you everyone who participated. We thank you the speakers, we thank you the organizers, we thank you the partner universities and partner organizations, and we very much thank you also the sponsors who helped us to make this happen. And we very much also thank you the Eastern European machine learning community who co-organized that with us. So huge thanks to you both. Yeah, I guess if there are any final words you'd like to say, please go ahead.
I would just like to thank you, Jeff and Dovydas, because you've done everything. Like in organization, it was all very easy for us. So yeah, I'm really happy that we got to meet you and collaborate with you. And I hope that we get to collaborate in the future again. So thank you so much.
Important thing to mention here, sorry, that it was not just Jeff and Dovydas, but it was also Linas from Lithuanian AI Association, who was helping arranging the speakers and coming up with all great ideas. I think it's also important to mention Daina from Vinted, who had awesome ideas in terms of how we should organize the streaming and the website. So yeah, that's also important to acknowledge.
I don't have much to add to what Viorica said. Thank you again. This was this was an awesome experience for me. I think I think that the workshop was quite interesting, and it was really well organized, and yeah, I'm happy I was part of it. So yeah, thank you.
I believe we can be wrapping up, unless Dovydas, you would like to add anything about the Lithuanian AI Association and for anything from the point of view of Lithuanian AI Association.
Yeah, just as I guess as everybody else said, it was amazing being here. It was amazing working with you guys, and I really hope that next year we'll have an even stronger event or more events with collaboration with you. So thank you all.
All right. Thank you, everyone, then. And we are wrapping up here. Thank you so much. Bye-bye to everyone.